2023, the James Webb Space Telescope looked back toward the earliest slice of cosmic time and photographed 6 galaxies. Each one contained stellar mass equivalent to tens of billions of suns. Each one existed just 500 to 700 million years after the Big Bang. And according to every simulation and mathematical model built over the preceding 3 decades, none of them should have been there. This was not a minor discrepancy. This was not a result sitting at the edge of the error bars. Astronomer Ivo Labbé and his team published the findings in the journal Nature, and shortly afterward, Mike Boylan-Kolchin at the University of Texas at Austin described the galaxies with 2 words: universe breakers. His analysis showed that even a single one of these objects, taken at face value, requires star formation efficiencies that violate how matter physically collapses under gravity. You cannot form stars faster than gravity allows. Gravity has a speed. These galaxies had apparently ignored it. Around the same time, John Mather, the Nobel Prize laureate, who had spent 20 years measuring the cosmic microwave background with the COBE satellite and received the Nobel Prize in Physics in 2006 for confirming the standard model of cosmology to extraordinary precision, made a public statement. Not in a peer-reviewed paper, not with error bars and method sections attached. He said 4 words: "This is not our universe." To understand why those words carry the weight they carry, you need to understand who Mather is in the field. He was not a critic of the standard model. He was not a competitor looking for weak points. He was the person who built the strongest confirmatory wall in the structure. He ran the instrument that weighed the foundation and signed off on it. When someone in that position says the structure does not match what he is looking at, that is not a critique from outside. It is something closer to a confession from inside. The field's response was not a press conference. It was not a coordinated rebuttal. What appeared instead was a particular kind of careful language in papers and statements from researchers across institutions. Words like unexpected, difficult to reconcile, and challenging our current understanding, which is how physicists say they do not know what to do with this yet. That specific silence, the absence of a confident counter-argument from anyone with comparable standing, has itself become informative. To understand what the telescope actually found, you need to understand what the standard model of cosmology predicted. The universe began approximately 13.8 billion years ago. In the first instance, matter was far too hot and energetic to form atoms. Protons and electrons existed separately in a hot plasma that was opaque to light. After roughly 380,000 years, the universe cooled enough for electrons to bind to protons, forming the first hydrogen atom. At that moment, light traveled freely for the first time. That light is still traveling. We detect it today as the cosmic microwave background, a faint thermal glow that fills the sky in every direction. From that moment forward, the standard model describes a universe that is gradually building structure from the bottom up. Small overdensities in the early plasma attract more matter through gravity. Dark matter halos collapse first, providing the gravitational wells into which ordinary gas falls. Gas condenses into the first stars. Stars live and die, scattering heavier elements across the surrounding medium. Later, generations of stars form chemically richer than the first. Over hundreds of millions of years, collections of stars merge and accumulate into galaxies. This process has a pace. The pace is set by the laws of physics, by how fast gravity pulls matter together, how fast stars live and die, how fast gas cools and collapses. The first generation of stars in this picture should have been chemically simple. Hydrogen and helium, the only elements the Big Bang directly produced. Heavier elements, carbon, oxygen, nitrogen, iron, do not exist in a young universe. They are manufactured inside stellar interiors through nuclear fusion and scattered into the surrounding space only when those stars die in supernova explosions. The gas that forms the next stellar generation is slightly enriched by those deaths. That generation lives, dies, and enriches the gas further. This cycle of stellar birth, nuclear burning, death, and chemical enrichment is called nucleosynthesis, and it has a timeline that physics sets and chemistry cannot override. What the James Webb Space Telescope found when it looked at the earliest observable epoch of the universe was that this timeline appeared to have been violated. Not in a subtle way. The galaxies Labbé's team photographed are not just heavier than they should be. When follow-up spectroscopic observations measured their chemical compositions, the spectra showed the presence of carbon, oxygen, and iron, elements that require multiple generations of stellar evolution to produce. elements that should not exist in detectable quantities at 500 million years after the Big Bang, because the stars needed to forge them had not yet had time to be born, live, and die. Picture a river delta. A river delta forms over tens of thousands of years as sediment accumulates. Channels shift, the system reaches its characteristic branching structure, and layers build from the bottom. The layers at the base record the beginning. The layers at the surface record the present. Now imagine finding a river delta where the deepest sediment is only 500 years old, but the delta has the layered complexity of something 10,000 years in the making. The layers are real. The dates are real. The timeline connecting them is not. That is the chemical situation the James Webb Space Telescope is documenting in the early universe. The first response from the scientific community was the correct one. Find the error. Astronomy has a reliable history of discovering measurement problems before concluding that known physics has failed. In 2011, a particle physics experiment appeared to show neutrinos traveling faster than light. The culprit turned out to be a loose fiber optic cable. In 2014, a radio telescope appeared to detect the signature of primordial gravitational waves. The signal was eventually traced to thermal emission from foreground dust that had been inadequately subtracted. The process of systematic error checking exists because it works. Teams examined the James Webb data from every direction. The calibration was checked against multiple independent standards. The redshift measurements, the technique that establishes both how far away a galaxy is and how far back in time it sits, were verified using two separate methods. Photometric redshift estimates the distance of an object by analyzing the pattern of colors in its light. Spectroscopic confirmation takes the next step, directly measuring specific emission lines in the galaxy's spectrum, lines produced by individual atomic transitions that are unambiguous and hard to fake. The 2023 spectroscopic follow-up campaigns targeted the most extreme photometric candidates and ran the direct test. The results did not shrink the sample, they confirmed it. The galaxies were real. They were where the telescope said they were. They contained what the photometry indicated they contained. Every methodological door that could have admitted a systematic error was tested. None of them were open. You are a cartographer who has spent 30 years making maps of a continent. Every instrument check passes. Every independent survey confirms the coastline. Then one day, you compare your finished map to an older one and discover the continent is in a completely different location than you assumed. Not because your instruments were wrong, but because the reference frame you calibrated them against contained an error none of your instruments could see. That is the category of problem the James Webb observations may have surfaced. Not a measurement error within the framework, but a question about the framework itself. What does it mean when every available adjustment moves a model closer to an observation without ever reaching it? Physicists tested this systematically. Step 1 was to push star formation efficiency to its theoretical maximum. In standard models, roughly 10% of available gas converts to stars in a given period. Some researchers tried models approaching 100% efficiency, every available atom becoming stellar fuel immediately. The galaxies Webb is finding still should not exist at the masses they display. Step 2 was to adjust the dark matter halo models that seed galaxy formation. Researchers modeled the most extreme halo concentrations that current dark matter physics permits. Still insufficient. Step 3 introduced exotic early physics, population 3 stars that were potentially thousands of times more massive than any star alive today, burning through their fuel in millions rather than billions of years. Better. Still not enough. Consider filling a swimming pool using a garden hose. The pool requires 1 million gallons. You have 6 months. You run the hose at full pressure every second of every day. You are still short by a factor of 10. Replacing the hose with a fire hydrant helps, but the pool still does not fill in the available time. That is the situation with early galaxy formation. Every efficiency gain available inside the existing model moves the numbers in the right direction. None of them moves the numbers far enough. There is a number called the Hubble constant. It describes how fast the universe is expanding, how quickly the distance between any 2 points in space grows with time. For most of modern cosmological history, measuring it precisely was considered the field's central practical challenge. 2 independent methods were being refined simultaneously. The assumption was that as precision improved, the 2 methods would converge on a single consistent value. The opposite happened. The Planck satellite measured the expansion rate from the cosmic microwave background, using the early universe as its starting point, and derived a value of 67.4 kilometers per second per megaparsec. Distance ladder measurements using Cepheid variable stars and type 1a supernovae as calibrated standard candles produced a value of 73.9 kilometers per second per megaparsec, 9% apart. Both measurements internally consistent, both independently verified, both running on the same physics, measuring the same universe, producing numbers that cannot simultaneously be correct. Picture two surveyors hired to measure the same river. One measures from the source working downstream. The other measures from the mouth working upstream. They use different equipment, different teams, different techniques. When they finish, their measurements of the river's total length should agree. If they disagree by 0.5%, you recalibrate. If they disagree by 9% after both teams have rechecked their instruments 3 times, you stop questioning the instruments. You start wondering whether both surveyors are measuring the same river. In 2019, Adam Rees, who had shared the Nobel Prize in Physics in 2011 for discovering that the expansion of the universe is accelerating, made a public statement about the Hubble tension. The discrepancy had passed 5 standard deviations. In particle physics, 5 sigma is the threshold for declaring a discovery. Rees was not announcing a discovery. He was announcing that the disagreement between the two measurements had grown too large to attribute to chance. He used a specific phrase, "Something is fundamentally wrong." That was before the James Webb Space Telescope launched, before the universe-breaker galaxies, before the dark energy spectroscopic instrument measured 6 million galaxies and found dark energy shifting. In 2019, Rees was describing one crack. By 2024, there were 4. One crack is a question. 4 cracks in 4 different walls of the same building are an answer about the foundation. To understand what the foundation is, you need to understand what lambda CDM actually describes. Lambda is the cosmological constant, the term in Einstein's equations that represents the energy density of empty space, the thing driving the accelerating expansion of the universe. CDM stands for cold, dark matter, the invisible mass that provides the gravitational scaffolding on which visible structure forms. Together, they describe a universe that is 5% ordinary matter, 27% dark matter, and 68% dark energy. A universe that expands at an accelerating rate and produces the large-scale structure we observe with a precision that, until recently, was considered one of the most successful frameworks in the history of science. Lambda CDM is not a working hypothesis. It is not a model under active revision. It is the operating system of modern cosmology, the framework inside which every simulation, every prediction, every statement about the universe's past and future is computed. The line between the model and reality blurred because the model kept working. Observation after observation confirmed it. The CMB power spectrum, galaxy clustering statistics, baryon acoustic oscillations, the abundance of light elements. The model worked so consistently that the question of whether it was accurately describing reality or just approximating it very well stopped feeling urgent. Consider what happens when a computer operating system has a hidden flaw. Every application functions normally. Every file opens. Every calculation completes. The flaw is invisible as long as no process demands something the operating system was not built to handle. Then one program makes an unusual request. The crash does not look like an operating system failure. It looks like a problem with that one program. You reinstall the program, it crashes again. You try a different program that makes the same request, same result. Lambda CDM is the operating system. The James Webb Space Telescope is the program making the request the system was not built to handle. In 2024, the Dark Energy Spectroscopic Instrument published results from a 5-year survey of 6 million galaxies. DESI mapped the 3-dimensional distribution of galaxies across cosmic history, using baryon acoustic oscillations as a standard ruler. Baryon acoustic oscillations are the fossilized imprint of sound waves that moved through the early universe plasma and left a characteristic scale in the clustering of matter. Measure that scale at different distances, and you reconstruct how the universe expanded at each moment, a frame-by-frame record of the expansion history. What DESI found is that the lambda and lambda CDM, the cosmological constant, the fixed number in Einstein's equations representing the energy density of empty space, does not behave like a constant. Its effective value shifts across cosmic time, at some epochs stronger, at others weaker. The published data across multiple papers, from an international collaboration of hundreds of physicists, shows a clear statistical preference for dynamical dark energy, a vacuum energy that evolves rather than sitting fixed throughout cosmic history. Think about a ship's navigator using a compass that gives consistent readings for years, then suddenly starts drifting. Every calculation made on the assumption of a fixed compass remains accurate for the period when the compass was stable, but every calculation made to project the ship's future position or to reconstruct where it was before the drift began is now wrong by an amount proportional to how much the drift matters. Lambda CDM is that compass. 6 million galaxies worth of measurement is the moment the navigator notes the drift. Every prediction Lambda CDM made about the future of the universe was built on a constant that appears not to have been constant, and the implications of a drifting dark energy extend further than the precision measurements. They extend to the question of how the universe ends. The standard picture assumed a fixed lambda and produced a specific trajectory. The universe expands forever at an accelerating rate. Galaxies drift apart until no light from one can reach another. Stars burn out. Black holes evaporate over incomprehensible timescales. What remains is cold, dark, and thermodynamically exhausted. This scenario is called the heat death. That picture required lambda to remain at its current value indefinitely. Lambda is not remaining at its current value. If dark energy grows stronger over time, if the drift DESI detected is in the direction of increase, the trajectory shifts dramatically. A sufficiently strong dark energy overwhelms every other force in sequence. First, it tears apart galaxy clusters, then individual galaxies, then solar systems, then planets, then atoms themselves. This scenario is called the Big Rip, a universe that does not fade slowly into darkness but shreds, with the final moments occurring faster than the speed of light can carry a signal from one side of a proton to the other. If dark energy weakens and eventually reverses, expansion slows and turns back into contraction. The universe collapses inward, the Big Crunch, a universe that ends where it began, or something like it. If dark energy oscillates in complex ways, the trajectory becomes something current models cannot reliably predict. 3 different endings corresponding to 3 different behaviors of one variable. The DESI data does not select one of these endings. What it selects is instability. Dark energy that is not where Lambda CDM said it was, and that may not stay where it is now. Dark energy has a name. It does not have an explanation. The cosmological constant appeared in Einstein's field equations in 1917, added by hand to prevent a static universe from collapsing under its own gravity. When Edwin Hubble demonstrated in 1924 that the universe was expanding, Einstein removed it, calling it his greatest blunder. When supernova observations in 1998 revealed that the expansion was accelerating rather than slowing, the cosmological constant was reintroduced and reinterpreted as the energy density of the quantum vacuum, the irreducible energy that empty space carries, even when no matter is present. Quantum field theory predicts that the vacuum should have an energy density. Virtual particle pairs pop in and out of existence everywhere in space, each pair briefly borrowing energy from the vacuum before annihilating. The sum of their contributions produces a baseline vacuum energy. Physicists calculated what that energy should be and compared it to the cosmological constant we actually measure. The predicted value is somewhere between 40 and 120 orders of magnitude larger than the observed value. That is a discrepancy of 10 to the power of 40 on the low end and 10 to the power of 120 on the high end. The largest discrepancy between a theoretical prediction and an observational measurement in the history of physics. Physicists named it the vacuum catastrophe. Consider a chemist who calculates how much heat a reaction should produce. She runs the experiment. The actual heat released is 100 billion times smaller than her calculation. She runs the experiment again. Same result. The reaction works. The product is correct. Everything observable is fine. And the theoretical prediction is wrong by a factor with no name in ordinary language. That is the vacuum catastrophe. Lambda works in every observation we make. The theory predicting its value is off by a factor that dwarfs every other failed prediction in science combined. Now, DESI is reporting that even the observable behavior of lambda is not what was assumed. What does it mean to build the standard model of cosmology on a term that cannot be derived from any deeper theory, and whose observed value contradicts quantum field theory by 120 orders of magnitude? In 1953, Fred Hoyle walked into a laboratory at Caltech and made a prediction that had no business being right. Hoyle was working on the problem of how heavy elements form inside stars. Carbon is the bottleneck. Without it, the chain of nuclear reactions producing oxygen, nitrogen, iron, and everything else in the periodic table cannot proceed. For carbon to form in stellar interiors, 3 helium nuclei must collide and fuse in a precise 2-step sequence. The probability of this happening under normal stellar conditions is almost impossibly low, too low to explain the abundance of carbon in the universe. And yet carbon is everywhere. In stars, in planets, in every living thing that has ever existed. Hoyle looked at that fact and worked backward. Carbon exists in abundance. Therefore, the reaction rate producing it must be far higher than raw probability suggests. Therefore, there must be a nuclear resonance state in the carbon-12 nucleus that dramatically enhances the reaction rate. He did not calculate this from quantum mechanics. He inferred it from the fact that we exist. He told the experimentalists at Caltech what energy level to look for. They looked. It was there. Not approximately there, not in the right neighborhood, but at almost exactly the predicted value. A value derived from no prior calculation, no prior measurement, no physical theory, derived solely from the premise that we are here, and therefore the universe must permit the chemistry that produced us. This reasoning, using the existence of observers to constrain physical parameters, is called anthropic reasoning. Brandon Carter formalized it in 1974 as the anthropic principle. We observe this universe because it is the kind of universe that produces observers. If the constants were different, we would not be here to notice. Logically airtight. Also, by itself, empty as a causal explanation. Saying we observe a life-permitting universe because only life-permitting universes contain observers is true in the same way that it is true that survivors of an accident are exactly the people who survived it. It describes a selection effect. It does not explain what selected. The question the anthropic principle addresses is what might be called the fine-tuning problem. There are approximately 26 fundamental constants in physics: the gravitational constant, the speed of light, the mass of the electron, the strength of the electromagnetic force, the strength of the strong nuclear force, Planck's constant, and others. These numbers determine the fundamental structure of reality. Together, they define how matter behaves, how energy flows, and whether the universe can produce anything more complex than hydrogen. What is striking is how sensitive the universe appears to be to the values of these constants. Reduce the strong nuclear force by 2% in either direction, and protons cannot bind into nuclei. Chemistry stops at hydrogen. No stars, no supernovae, no heavy elements, no carbon, no planets. Nothing with the complexity to ask why. Increase the cosmological constant by a factor of a few hundred above its observed value, and the universe expands so rapidly after its initial moment that matter never gravitationally collapses into structures. No galaxies, no stars, nothing. Shift the ratio of the electromagnetic force to gravity by 1 part in 10 to the power of 40, a number whose smallness is genuinely difficult to communicate in words, and stars either burn through their fuel in millions rather than billions of years, too fast for planetary chemistry to develop, or they never ignite at all. Change the mass of the electron by a few percent, and the chemistry of DNA becomes impossible. Change Planck's constant and atomic structure dissolves. Picture a combination lock with 26 dials. Each dial runs from 0 to a trillion. The lock opens only when all 26 are set to specific values. Not approximately, not within a range, but precisely. The probability of hitting the right combination at random is a number so small it has no useful analogy in human experience. But here's what makes the physical situation stranger than a combination lock. The dials are not set by anyone turning them. They appear to have come preset from the beginning at the values required. What kind of universe arrives, with its combination already dialed in? 3 explanations exist for why the constants have the values they do. Each, followed honestly to its conclusion, requires giving something up. The first is the anthropic principle in its simplest form. We observe a life-permitting universe because we exist. It explains nothing about why this particular combination of constants was drawn. It simply identifies that it was. The second explanation requires accepting that our universe is one member of an enormous ensemble of universes, each with different constants drawn from the same underlying process. In an ensemble large enough, every combination gets tried. We live in one that worked by chance, because only the ones that work can contain observers to notice. This explanation is scientifically motivated. It falls naturally out of inflationary cosmology. It is also unverifiable in principle, because the other members of the ensemble lie beyond any boundary we can ever cross. The third explanation is that the constants are not fundamental free parameters at all. A deeper theory will eventually show that their values follow necessarily from mathematical first principles, the way 2 + 2 = 4 follows from the axioms of arithmetic, rather than from anyone choosing to make it that way. This is the most conservative option and the one with the least evidence currently pointing toward it. What is notable is that the second explanation, the multiverse, was not invented to address fine-tuning. It arrived as a mathematical consequence of a theory accepted for entirely different reasons. Inflation was proposed in 1981 by Alan Guth to solve two specific technical problems with the standard cosmological model. The first was the horizon problem. The universe appears almost perfectly uniform at the largest scales, with temperature variations of only 1 part in 100,000 in every direction. But regions on opposite sides of the observable universe have never been in causal contact. They could not have exchanged energy or information to reach thermal equilibrium. They are simply identical. The second was the flatness problem. The geometry of the universe is spatially flat to extraordinary precision. Maintaining that flatness from the earliest moments to the present requires the initial energy density to have been fine-tuned to 1 part in 10 to the power of 60. Guth's solution was that in the first fraction of a second, the universe expanded exponentially fast, stretching everything into contact before the accelerated expansion began, then freezing the geometry flat. It worked. The cosmic microwave background confirmed his predictions with remarkable precision. Nobody initially asked what inflation does if it does not stop everywhere at once. Andre Linde asked in 1983. He showed that in most versions of inflationary theory, inflation does not stop globally. It stops locally in patches while continuing elsewhere. The inflating regions generate new stopping patches, each with slightly different physical properties set by quantum fluctuations at the moment when inflation ended locally. Those patches generate more inflating regions. The process has no global end. It is self-reproducing and eternal, producing an effectively infinite number of post-inflationary regions, each a separate universe, with its own values for the 26 constants, each with its own physics. We did not choose the multiverse. We chose inflation. The multiverse arrived as a mathematical consequence of the mechanism accepted to explain the smoothness of the sky. String theory introduces an additional layer to this picture. Physicists working to unify quantum mechanics and general relativity, the two most successful and mutually inconsistent theories in physics, found that the mathematics of string theory requires extra dimensions, 6 or 7 spatial dimensions beyond the 3 we experience, curled up at scales far below anything we can probe with current technology. The geometry of those extra dimensions determines the physical constants of the resulting universe. Different geometries, different constants. The number of possible geometrical configurations consistent with string theory mathematics is approximately 10 to the power of 500. Not an estimate, but the result of systematic counting. 10 to the power of 500 possible sets of physical laws, each one a valid solution to the same equations. Physicist Leonard Susskind called this the landscape. What this means, taken seriously, is that the concept of a law of nature requires redefinition. If the landscape is real, our 26 constants are not universal laws. They are local conditions. The values we measure are the values our region of the multiverse drew when inflation ended here. Other regions drew other values. The physics we have spent centuries discovering is the physics of this address. If bubble universes are real and they collide, the collisions should leave observable signatures. When two expanding bubbles intersect, the collision deposits energy on their shared boundary, leaving a circular feature in the cosmic microwave background with a specific temperature profile that differs from the surrounding background. This is a testable prediction. The CMB has been mapped to extraordinary precision by the Planck satellite. There is a feature in the CMB called the cold spot, located in the direction of the constellation Eridanus. It is a region significantly colder than the average background, large enough and statistically anomalous enough that standard inflationary models produce it by chance in roughly 2% of realizations. 2% is not impossible, but 2% sitting alongside other anomalies that each individually fall at the edge of statistical expectation starts to accumulate weight. The cold spot has a specific temperature profile, a central depression surrounded by a ring of relative warmth that several research groups have noted is consistent with the signature expected from a bubble collision. A neighboring region of space-time that intersected ours in the first instant of cosmic history, depositing its boundary energy on our sky, leaving its fingerprint in the temperature map we have now measured for 30 years. The cold spot has other explanations. A large void in the foreground, a statistical fluctuation. The debate is not settled. What is settled is that the feature exists, that it is anomalous, and that one of its physically valid explanations is that we are looking at the imprint of contact with another universe. Alongside the early galaxy problem and the Hubble tension, there is a third observational anomaly worth examining carefully. In the 1950s, Enrico Fermi was having lunch with colleagues at Los Alamos and asked a question that has not been resolved in the decades since. The galaxy is old enough and large enough that if technologically capable life arises with any meaningful probability, it should be visibly and pervasively present. The galaxy is approximately 13 billion years old. At modest assumptions about the probability of life and the timescales of technological development, even civilizations that spread at just a small fraction of the speed of light could have populated the entire galaxy many times over in the time available. The sky is silent. Frank Drake formalized this question in 1961 at a meeting in Green Bank, West Virginia, writing an equation on a blackboard to organize what the group would need to estimate in order to calculate how many communicating civilizations might exist. Star formation rate, fraction of stars with planetary systems, fraction of those with habitable conditions, probability that life arises, probability that intelligence develops, probability that intelligence develops detectable technology, and the average lifetime of a civilization that is actively transmitting signals detectable at stellar distances. Multiply these together, and you get an estimate. Drake's original calculation produced a number in the range of 10 civilizations in the Milky Way. It was a framework for thinking, not a precise result. The factors varied widely in their certainty. What the James Webb Space Telescope has done is begin to measure some of those factors directly. Data from the Kepler Space Telescope put the frequency of planetary systems around Sun-like stars very high, with roughly 1 in 5 hosting a planet in the habitable zone. James Webb has detected water vapor, carbon dioxide, and sulfur dioxide in the atmospheres of exoplanets. Every factor that telescopes can touch has moved the Drake equation toward a larger estimate for the number of civilizations. Every factor that telescopes cannot touch, whether life actually arises from chemistry, whether intelligence develops from biology, whether civilizations survive long enough to transmit, carries all the explanatory weight for why the answer appears to be approximately 0. Think about an accountant auditing a company. She can verify every item on the revenue side. All of it checks out. But the company keeps posting losses attributed to operating costs that are unitemized and unverifiable, simply large enough to erase whatever the revenue side produces. The Drake equation works the same way. The revenue side is being audited by telescopes, and it is healthy. The loss side is a single unitemized line that erases it all. In 1998, Robin Hanson published a paper titled, "The Great Filter, Are We Almost Past It?" The Great Filter is whatever step between the conditions for life and the evidence of intelligence is so difficult that the galaxy is empty despite being old enough and large enough to be full. The question is not whether a filter exists. The silence is itself evidence that something filters. The question is where the filter sits relative to where we are. If the filter is behind us, the hard step is something in our past. The origin of life from chemistry, the emergence of eukaryotic cells from prokaryotes, the development of multicellular organisms, the evolution of intelligence. We are among the rare successes that made it through. The galaxy is silent because the hard step is a barrier most life does not cross, and we crossed it. This is the interpretation that should be preferred if we discover that life in the universe is rare. If the filter is ahead, the hard step is something we have not yet attempted. The galaxy is quiet not because intelligent life rarely reaches our stage, but because most intelligent life that reaches our stage does not survive what comes next. We are not a rare beginning. We are a typical civilization approaching a typical end. This is the interpretation that should be feared if we discover that life in the universe is common. What the James Webb Space Telescope is demonstrating, with each new exoplanet observation confirming a habitable environment, and each new atmospheric detection confirming the chemical prerequisites for biology, is that the conditions for life appear to be widely distributed. which is precisely the information that sharpens the danger of the great filter interpretation. Every additional habitable world confirmed is another planet that apparently made it to the starting line. And if there are many who made it to the starting line, the finish line must be somewhere most of them never reach. Fermi asked his question as a puzzle about astronomical history. James Webb is turning it into a question about our future. In 1972, Jacob Bekenstein was a graduate student at Princeton, wrestling with a problem that seemed, at first, to be a bookkeeping problem in thermodynamics. The second law of thermodynamics states that entropy, a measure of disorder, never decreases in a closed system. But black holes appear to violate this. Drop matter into a black hole, and the entropy of that matter vanishes behind the event horizon, apparently destroyed. Bekenstein proposed a resolution stranger than the problem it was solving. Black hole entropy is proportional to the area of the event horizon, not its volume. Information is written on the boundary, not stored in the interior. Stephen Hawking confirmed this and extended it, showing that black holes emit thermal radiation through a quantum mechanical effect near the event horizon, a result now called Hawking radiation. The discovery initially seemed to make the information problem worse. Thermal radiation is structureless. It carries no information about what produced it. If everything that falls into a black hole eventually leaves as featureless thermal radiation, the information is gone. The argument over whether information can truly be destroyed ran for 3 decades. The resolution came from extending Bekenstein's insight into a broader principle called holography. If information is stored on the boundary of a region, rather than in its volume, then as matter crosses the horizon, its information is encoded there, not destroyed. In 2004 in Dublin, Hawking publicly conceded the point, acknowledging that information leaks out encoded in subtle correlations in the Hawking radiation. In principle, recoverable. In practice, extraordinarily difficult to read, but not destroyed. The universe does not destroy information. The past is, in a precise technical sense, permanent. In 1997, Juan Maldacena published a result that has since been confirmed across thousands of papers over nearly 30 years. He showed that a specific theory of gravity in a curved spacetime is exactly equivalent, not analogous, but mathematically identical, to a quantum field theory living on the boundary of that spacetime. This correspondence is called ADS, CFT, and what it implies, taken seriously, is that gravity is not fundamental. Spacetime geometry, the curvature that holds galaxies together, bends light, and defines distance, is not a stage on which physics happens. It emerges from physics happening on a boundary. Compare this to temperature. Temperature is real. It is measurable. It has causal effects. But it is not a fundamental constituent of nature. It emerges from the collective behavior of particles. It would not exist if you described each particle individually. ADS, CFT, suggests that space is like temperature, emerging from quantum entanglement between degrees of freedom that do not themselves live in space. Mark van Ramstonk published a paper in 2010 containing a thought experiment that deserves more attention than it has received outside the theoretical physics community. Take 2 quantum systems, call them A and B, and make them maximally entangled. In the ADS CFT framework, this corresponds to a connected space-time, a geometric bridge between the 2 regions. Now reduce the entanglement. The geometric bridge gets longer and thinner. Reduce the entanglement to 0 and the bridge closes. The 2 regions are no longer geometrically connected. The space between them is not empty. There is no space between them. Removing the entanglement does not move them apart. It destroys the connection that made apart a meaningful concept. What Van Ramsdonk's result says is that space is not a container. It is a consequence of quantum correlations. Remove the entanglement, and you do not get distant space. You get no space. The space you occupy right now exists as a consequence of quantum relationships between underlying degrees of freedom that do not themselves live in space. The medium you exist in is not a given. It is emergent. Physics has a pattern. When a small anomaly survives every explanation the existing framework can offer, the resolution eventually costs the framework itself. For 50 years, there was a problem with the orbit of Mercury. Mercury precesses. Its elliptical orbit rotates slowly after each complete revolution. Newtonian mechanics makes a precise prediction about this. When astronomers subtracted the calculated contributions of planetary gravitational perturbations from the observed precession, A residual remained, 43 arcseconds per century, small enough that only dedicated instrumentation could detect it, large enough to sit stubbornly in the literature without a theoretical home. Proposals accumulated. An undiscovered planet interior to Mercury's orbit, which astronomers named Vulcan. Searches were conducted. Vulcan was not found. A slight oblateness in the sun. Measurements were attempted. The sun proved round enough. Every explanation within the Newtonian framework produced at least one additional problem. The number sat there for 50 years, theoretically homeless. In 1915, Einstein completed general relativity. One of his first calculations was Mercury's perihelion precession. The result was 43 arcseconds per century. Exactly. Without free parameters, without adjustment, the number that had been theoretically homeless for 50 years fell directly out of a theory built on fundamentally different conceptual foundations. Not modified gravity, not corrected Newtonian mechanics, but a reconceptualization of what gravity is. The cost of explaining 43 arcseconds was the Newtonian framework. The Hubble tension is 9%, 2 orders of magnitude larger than the Mercury discrepancy. The early galaxy problem sits outside every parameter adjustment that has been tried. The DESI dark energy result rewrites the fate of the universe. The Hercules Corona Borealis Great Wall, a filamentary structure approximately 10 billion light-years in extent, exceeds by roughly 10 times the scale above which the universe is required to be homogeneous. Its existence either means the cosmological principle is wrong, which means lambda CDM is built on a false foundation, or it requires physics absent from every model currently on the table. Each of these anomalies is theoretically homeless right now, in the same position that Mercury's precession occupied in 1865. 3 broad directions exist for what might come after lambda CDM. None have won. The first modifies gravity directly, attempting to reproduce the successes of the standard model without dark matter. These approaches produce some successes. They struggle with the bullet cluster, 2 galaxy clusters that collided and passed through each other, with their hot gas slowed by electromagnetic drag, while the mass distribution continued forward. The spatial offset between the gas and the mass is precisely what dark matter predicts, and precisely what modified gravity cannot cleanly reproduce. The second direction keeps the general framework and adds ingredients. Early dark energy, a brief burst of additional energy density in the first 100,000 years, shifts the CMB-derived expansion rate upward, reducing the Hubble tension. Models incorporating it close some of the gap. They introduce new tensions elsewhere. Every added ingredient solves one problem and creates pressure somewhere else. The third direction replaces the substrate. Loop quantum cosmology replaces the Big Bang singularity with a quantum bounce. Causal set theory replaces continuous spacetime with a discrete structure at the Planck scale. Not adjustments to the standard model, but replacements for the spacetime framework on which the standard model is written. These approaches are not yet complete enough to make the full range of cosmological predictions lambda CDM can make. In 2023, a team at Johns Hopkins published a conclusion about the Hubble tension and the standard model. Not that it was difficult, not that it would require more data. They concluded that reconciling the 2 measurements within the existing framework cannot be done. That paper sits alongside Labbé's universe breakers, Ries's 5 sigma warning, and DESI's drifting constant. 4 independent groups, 4 independent conclusions, all pointing at the same place. The physics we know describes a region, not the universe. What James Webb will continue doing until at least 2041, when its fuel reserves are expected to allow continued operation, is accumulating data. Each year of additional observation extends the scientific return on the $10 billion investment significantly. In 2022 and 23, it found massive early galaxies that broke every simulation. In the years since, it has measured atmospheric chemistry on exoplanets. It imaged the most distant individual star ever observed, a blue supergiant at a redshift of 6, existing when the universe was less than 1 billion years old. Each of these results was a test. Each came back with something the model did not predict. Think about a doctor who orders a series of tests, expecting to rule out a rare condition. The first test comes back unusual, the second unusual in a different way. The third, fourth, fifth, each unusual, each in a different direction, together forming a pattern that no longer looks like coincidence. James Webb is that series of tests. Each individual result has an alternative explanation. The accumulation has a shape. The shape is not the shape of a healthy lambda CDM universe. The standard model of cosmology is built on a prerequisite called the cosmological principle. The assumption that the universe looks the same everywhere, at the largest scales, that no location is preferred over any other. This is not a prediction the model makes. It is the ground the model stands on. Remove the assumption, and the equations that produce lambda CDM do not apply. And yet the cosmological principle has never been directly confirmed at the scales where it matters most. Everything we call observational confirmation was gathered from inside our observable bubble, a sphere roughly 93 billion light-years across. We built models as if they described everything. We took measurements from inside our sphere, extracted what looked like universal laws, and applied those laws to regions we cannot observe and will never observe. The observable universe is a sphere defined not by the universe's actual size, but by the speed of light and the age of the universe. Everything outside it is receding faster than light can return from it. The boundary is physical, and everything we call cosmology was built from data collected inside it. The problem is that we did not build our models as if they were local. We built them as if they described everything. Inflation makes this sharper. Eternal inflation implies our observable sphere is one patch in a self-reproducing structure with no global edge and no global physics. The 26 constants are what our patch drew when inflation ended here. Other patches drew other values. The laws we measured are the laws of this address. A cartographer spends 40 years mapping one continent. The maps are extraordinary, precise, verified, correct about every road and river. Then, someone shows him a satellite image. The continent is one landmass among 7. Everything on his maps is accurate. None of it describes the ocean. The maps were not wrong. They were local. Lambda CDM is the map of the continent. James Webb is the first satellite image. Each time, physics has acknowledged that our position is less central than assumed. What followed was an expansion of what could be understood. In 1543, Copernicus published the argument that Earth moves around the Sun. The resistance to it came partly from what accepting heliocentrism meant, that Earth was not the center, that our location was not privileged. What followed was Newtonian mechanics, the first mathematical description of the physical universe. In 1924, Hubble demonstrated that the Milky Way is one galaxy among roughly 2 trillion. What followed was the discovery of the expanding universe, the Big Bang, and the whole architecture of modern cosmology. The cosmological principle generalized that logic. We occupy no preferred location in the universe. What followed was lambda CDM and 30 years of precision cosmology. The step happening now is the recognition that our laws may not be universal. They may be local. The physics we have measured describes the region accessible from our location, governed by the constants our bubble drew during inflation. Within that region, the physics is accurate. The equations work. What they are not is necessarily universal. Every time physics acknowledged that our position is less central, it gained something in return. Copernicus produced Newton. Hubble produced the Big Bang. The cosmological principle produced lambda CDM. If the pattern holds, then the recognition that our laws are local should produce something that can work at the scale the current model cannot reach. What that framework will look like, no one currently knows. The resolution is not in the existing 3 directions. Each of them has been tested against the full dataset, and none closes all 4 anomalies simultaneously. Whatever comes next is probably not an extension of any of them. The resolution comes from outside the frameworks entirely, the way general relativity came from outside Newtonian mechanics. What we do know is what the evidence is saying. The James Webb Space Telescope found galaxies that the standard timeline cannot explain. That timeline runs on lambda CDM. Lambda CDM depends on a cosmological constant that 6 million galaxies measured by DESI show is not constant. A drifting constant means the vacuum energy is dynamical. Quantum field theory predicts the vacuum energy should be 120 orders of magnitude larger than what we measure, the biggest failed prediction in physics. The 26 constants are tuned with a precision that random chance cannot produce in a single universe. Explaining them requires either an infinite ensemble of universes, which falls naturally out of the inflationary theory accepted to explain the smooth CMB, or a deeper theory that has not yet been found. If the ensemble is real, our constants are local. Local constants mean local laws. Local laws are consistent with the holographic principle, and ADS, CFT. Gravity emerges from quantum physics on a boundary. Emergent gravity is consistent with Van Ramstonk. Space-time connectivity is a consequence of quantum entanglement. Remove the entanglement and space stops existing. Every link in the chain holds. The chain ends not at an answer, but at a boundary, the limit of what physics can currently say. What sits at that boundary is a universe that appears to run on universal laws that turn out to be local. A space-time that feels fundamental, but emerges from quantum relationships that do not themselves live in space. A vacuum energy that should be enormous, but is almost exactly zero in ways that no existing theory explains. An expansion rate that two precision measurements cannot agree on. Galaxies in the early universe that should not exist but do. A silence in the sky where other civilizations should be transmitting. And inside all of that, on one planet, in one galaxy, in one bubble of a potentially infinite self-reproducing space-time, something that notices, something that builds a $10 billion telescope and points it at the beginning of time, and finds that the beginning does not match the model. The telescope is still running. The data is still arriving. The James Webb Space Telescope will continue returning observations until at least the early 2040s. Each new deep field image, each new spectroscopic measurement of an early galaxy, each new confirmation of atmospheric chemistry on a distant planet adds to a data set that is already telling a consistent story. The story is not that the universe is mysterious in some vague or poetic sense. The story is that four independent lines of evidence, measured by different instruments using different techniques and analyzed by different teams, all point at the same foundational assumptions of the standard model, and none of them confirm those assumptions. In the current moment, between when an old answer is known to be insufficient and when a new answer has arrived, researchers are working on several fronts simultaneously. On the observational side, the Euclid Space Telescope, launched by the European Space Agency in 2023, is conducting a wide-field survey of billions of galaxies designed specifically to constrain the properties of dark energy with greater precision than any previous instrument. Its data will eventually provide an independent test of whether the dark energy drift detected by DESI is real and how it behaves over cosmic time. On the theoretical side, physicists working on quantum gravity are attempting to extend ADS, CFT correspondence, beyond its original domain to see whether the mathematical equivalence between a gravitational theory and a boundary quantum field theory can be made to apply to a universe with a positive cosmological constant, which is what we actually live in, rather than the negatively curved space the original formulation addressed. Progress has been slow and the mathematics is difficult, but if the correspondence can be generalized, it would provide a framework in which space and gravity are derived, rather than given, potentially offering a new foundation for cosmology. On the question of dark matter, several experiments worldwide are reaching sensitivities that will either detect the most theoretically favored dark matter candidates or rule them out definitively, forcing the field to either embrace more exotic dark matter models or take more seriously the alternatives that modify gravity directly. What is not known is whether any of these efforts will produce a clean resolution or whether the resolution will come from an entirely unexpected direction, as it has done repeatedly in the history of physics. The photoelectric effect that led to quantum mechanics was not predicted by any of the theoretical frameworks trying to resolve the ultraviolet catastrophe. General relativity came from thinking about the equivalence of acceleration and gravity, not from trying to fix Mercury's precession. The structure of DNA came from X-ray crystallography, applied to a molecule that most physicists in 1950 were not focused on. The history of physics is not a history of problems solved by the frameworks that identified them. It is a history of frameworks replaced by new ones that came from directions no one was looking. John Mather said, "This is not our universe," based on what the telescope showed him. He was not being metaphorical. He was not being dramatic. He was describing the specific content of the data from an instrument he helped design and helped operate in the context of a standard model he spent his career helping to confirm. The four words carry the weight of that context. They are the building inspector, after certifying the foundation, standing outside saying something is wrong with the structure. Whether the problem is with the timeline of cosmic evolution, with the behavior of dark energy across cosmic history, with the assumption that local laws are universal laws, or with something deeper about what space and time actually are, remains to be determined. What is no longer reasonable to assume is that the existing framework, extended without modification, will eventually accommodate all four anomalies. Each of them has been stress-tested carefully. Each of them has survived. Together, they represent a level of systematic divergence between the standard model and observational reality that, in the history of physics, has always preceded a fundamental revision. The telescope is looking, the data is accumulating, and the gap between what the standard model predicts and what the universe is showing us is not narrowing. It is becoming, with each new observation, more precisely defined. That precision is the progress, not the answer, but the sharpening of the question, until the question itself becomes a kind of guide. The universe is under no obligation to fit the models built to describe it. What it is under, and what the data increasingly demonstrates, is the obligation to be consistent with itself. Every anomaly is the universe being consistent with something the model missed. Finding what that something is, at the scale where quantum mechanics and gravity and the large-scale structure of space itself all have to be reconsidered together, is the work of the coming decades. And it is possible, though not guaranteed, that whoever does it will stand in the same position Albert Einstein stood in when he sat down to calculate Mercury's precession in 1915, and watch the number come out right. The moment when the homeless anomaly, the number that has been sitting without a theoretical address for decades, suddenly has somewhere to go. The moment when the framework that can explain it already also explains, without adjustment, everything the previous framework explained. That moment has not arrived. The data that will force it is arriving now. To understand the depth of the crisis in modern cosmology, it helps to trace how the standard model was built and why it earned the confidence it held for so long. The story begins not with a telescope, but with a thought experiment that Albert Einstein published in 1915, embedded in the mathematics of general relativity. Einstein's field equations described how matter curves space-time and how that curvature determines the motion of everything within it. When applied to the universe as a whole, the equations had a troubling implication. The universe could not be static. It had to be either expanding or contracting. Einstein was so uncomfortable with this implication that he added a term to his equations by hand, a constant that provided a kind of cosmic repulsion to balance the gravitational attraction and allow a static universe. He called it the cosmological constant, represented in his equations by the Greek letter lambda. Then Edwin Hubble looked through the telescope at Mount Wilson. Hubble had been working on the question of whether the fuzzy patches called nebulae were objects within our galaxy or separate galaxies at enormous distances. In 1924, he identified Cepheid variable stars in the Andromeda Nebula, stars whose intrinsic brightness is tied to their pulsation period in a precise and measurable relationship. By comparing the known intrinsic brightness of these stars to their apparent brightness as seen from Earth, he could calculate their distance. The answer was 800,000 light-years, far beyond any plausible distance within the Milky Way. Andromeda was a separate galaxy. Then, combining his distance measurements with Vesto Slipher's earlier observations of the redshifts of galaxies whose light was stretched toward the red end of the spectrum by the Doppler effect of recession, Hubble found a pattern. The more distant a galaxy, the faster it appeared to be receding, in every direction. The universe was not static, it was expanding. Einstein removed the cosmological constant from his equations. He would later describe this as his greatest blunder. But the expanding universe implied something extraordinary when you ran it backward. If the universe is expanding in every direction today, then at earlier times it must have been smaller, denser, and hotter. Run the clock far enough back, and you reach a moment when everything in the observable universe was compressed into a state of extraordinary density and temperature. This was the beginning. Georges Lemaitre, a Belgian priest and physicist, had actually proposed this idea before Hubble's confirmations, calling the initial state the primordial atom. The idea was resisted for decades. Fred Hoyle, the same physicist who would later use the existence of carbon to predict a nuclear resonance, was among its most prominent critics. In a 1949 radio broadcast intended to describe and dismiss the idea, Hoyle called it the Big Bang. The name stuck, somewhat ironically, long after Hoyle's alternative steady-state model was discredited by observations. The confirmation that settled the debate came in 1964 and was accidental. Arno Penzias and Robert Wilson were engineers at Bell Laboratories trying to calibrate a large communications antenna. They kept detecting a faint microwave signal that came uniformly from every direction and refused to go away. They checked for instrumentation errors. They cleaned the antenna, removing a coating of what they diplomatically described as white dielectric material left by pigeons nesting inside it. The signal persisted. A colleague told them about a Princeton group working on the theoretical prediction that a hot Big Bang should have left behind a bath of thermal radiation that had cooled to approximately 3 degrees above absolute zero as the universe expanded. That is exactly what Penzias and Wilson had found. They had discovered the cosmic microwave background by accident while trying to eliminate noise from a satellite dish. They received the Nobel Prize in Physics in 1978. The cosmic microwave background became the foundation on which precision cosmology was built. John Mather's COBE satellite, launched in 1989, mapped the temperature of the CMB across the entire sky. What it found matched the predictions of the Standard Model with extraordinary precision. The temperature varied by only 1 part in 100,000 from point to point, and the pattern of those variations encoded the initial conditions of the universe in a way that could be calculated and compared with theory. The agreement was striking. Mather received the Nobel Prize in Physics in 2006, shared with George Smoot, who led the analysis of the angular structure in the COBE data. The Wilkinson Microwave Anisotropy Probe, launched in 2001, refined the measurements further, and the Planck satellite, launched in 2009, refined them further still. With each generation of measurement, the Standard Model accommodated the data with increasing precision. Lambda CDM emerged as the consensus because it consistently worked. Its success was not theoretical, it was observational. The theory that keeps working when tested is the one you adopt, and Lambda CDM kept working for 30 years. What changed was the instruments. The James Webb Space Telescope represents a leap in observational capability that is not incremental, but transformative. Webb's primary mirror is 6.5 meters in diameter, compared to 2.4 meters for the Hubble Space Telescope. More significantly, Webb operates primarily in the infrared, the part of the electromagnetic spectrum where the most distant and therefore most ancient objects appear, because the expansion of the universe has stretched their light far beyond its original wavelengths. An object at a redshift of 7, meaning the universe is expanded by a factor of 8 since that light was emitted, appears not as visible light, but as infrared radiation. Hubble could not efficiently detect it. Webb can. Webb was also positioned at the second Lagrange point, 1,500,000 kilometers from Earth in the direction away from the Sun, a gravitationally stable location that allows the telescope's infrared detectors to be cooled to operating temperatures below 40 degrees Kelvin, approximately minus 230 degrees Celsius, by a large sunshield the size of a tennis court. This thermal stability is what allows the detectors to operate with the sensitivity required to observe objects at the edge of the observable universe. When Webb was launched in December of 2021 and began returning first science images in the summer of 2022, the results were immediately striking. The first deep field images showed thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length. More strikingly, many of those galaxies were far more massive and far more structured than the Standard Model predicted for objects at that epoch. The reaction within the research community was initially cautious. Photometric redshift estimates, which rely on the pattern of colors in a galaxy's light rather than direct spectroscopic measurement, are subject to uncertainties. A galaxy that appears to be at a very high redshift based on photometry might, upon more detailed spectroscopic examination, turn out to be at a lower redshift, with unusual spectral characteristics that mimic the photometric signature of a distant object. This would make the galaxy less distant, less ancient, and therefore less problematic for the Standard Model. The spectroscopic follow-up campaigns, conducted through 2023, were specifically designed to test this possibility. The results, published in multiple papers by multiple independent teams, confirmed the photometric redshifts. The galaxies were where Webb said they were, and they were as massive as the photometry indicated. This matters because the spectroscopic confirmation closed the most straightforward route to explaining away the discrepancy. Redshift is not ambiguous when it is measured directly from emission lines in a galaxy's spectrum. The emission lines of hydrogen, oxygen, and other elements occur at specific wavelengths determined by atomic physics. When those lines are observed at longer wavelengths than their laboratory values, the ratio of observed wavelength to laboratory wavelength directly gives the redshift, and therefore the distance and age of the source. There is no calibration involved that could systematically shift the result by a large factor. The universe breaker galaxies were real, Boylan-Kolchin's analysis of what this means for the Standard Model is worth examining in detail. In the Standard Model, the formation of galaxies is seeded by dark matter halos, regions where dark matter density is slightly higher than the average, and therefore gravitationally attracts additional matter. The distribution of dark matter halos at any given time is one of the most precisely calculated quantities in modern cosmology, derived from the spectrum of density fluctuations visible in the CMB, and evolved forward in time using the known equations of gravity. For a galaxy of a given stellar mass to exist at a given redshift, there must be a dark matter halo massive enough to contain it, and the ordinary matter inside that halo must have had enough time to cool, collapse, and convert a significant fraction of itself into stars. Both of these conditions are quantifiable. The first requires knowing the mass function of dark matter halos, which is calculated from simulations and matches CMB observations well. The second requires modeling the efficiency of star formation, which is constrained by observations of galaxies in the local universe and at intermediate redshifts. What Boylan-Kolchin showed is that the 6 galaxies in Labbé's sample require not just high star formation efficiency, but efficiencies that violate the physical limits on how quickly gas can cool and fragment into stars. The limit is called the freefall time, the timescale on which gas in a region of given density collapses under its own gravity. You cannot form stars faster than the freefall time allows, any more than you can fill a tank faster than the rate at which water can flow through the pipe feeding it. The pipe has a physical cross-section. Gas collapse has a physical timescale. These galaxies had apparently converted gas into stars faster than the timescale permits. There is a second constraint that Boylan-Kolchin applied, which is the total budget of matter available. In the Standard Model, the total amount of matter that can collapse into any structure by a given time is determined by the expansion rate of the universe, the amplitude of the initial density fluctuations, and the growth factor, which describes how those fluctuations have grown. This is a budget, and the 6 galaxies in Labbé's sample together contained more stellar mass than the entire universe's budget allowed for structures of that kind to have produced by that epoch. Imagine a factory operating for 2 years that produces 10 times more finished goods than the supply chain could have delivered raw materials for. The most direct conclusion is that something is wrong with your accounting. Either the goods were actually produced over a longer period and you have mislabeled the dates, or they were produced somewhere else and you have mislabeled the origin, or the supply chain was far larger than you thought. The spectroscopic measurements ruled out the first 2 possibilities in the galactic case. That leaves the third. The chemical evidence provides a second and independent confirmation of the same conclusion. When a galaxy spectrum is measured in sufficient detail, it reveals not just the overall continuum of light from billions of stars, but the specific absorption and emission features of individual elements. The relative strengths of these features give the chemical abundances, how much carbon relative to oxygen, how much iron relative to hydrogen, and so on. In the local universe, the chemical abundance patterns of galaxies follow a progression from the most ancient and chemically simple to the most recent and chemically complex. Old stars in the outskirts of galaxies contain very little iron compared to hydrogen, a ratio astronomers call metallicity. Young stars in the central regions of actively forming galaxies are more metal-rich, reflecting the cumulative output of multiple stellar generations. The metallicity of a galaxy's stellar population is a record of its chemical history. What the James Webb spectra of early universe galaxies show is that some of these objects have metallicities significantly higher than expected for their epoch. They contain measurable quantities of elements that require several stellar generations to produce. And those stellar generations, each one a cycle of birth, nuclear burning, and explosive death over timescales of millions to hundreds of millions of years, all had to have happened before the galaxy itself was old enough to exist in the Standard Model. The chemical evidence and the mass evidence are not from the same technique. Masses come primarily from the total brightness of the galaxy combined with stellar population models. Chemical abundances come from spectral line ratios. They are measured differently, subject to different systematic uncertainties, and they agree. Something processed more material through stellar evolution in the early universe than the timeline allows. This is worth pausing on. In science, when 2 independent lines of evidence, measured by different instruments, using different techniques, converge on the same conclusion, that convergence is informative in a way that neither line alone could provide. Each might have its own systematic errors, but it becomes increasingly unlikely that two independent systematic errors would conspire to produce the same wrong answer. The mass problem and the chemical complexity problem share a single root. The universe processed matter through stellar evolution at a rate the standard timeline cannot accommodate. Now consider what happens when this evidence is combined with the Hubble tension, the 9% disagreement between the two methods of measuring the expansion rate of the universe. The Hubble tension has its own internal structure that is worth understanding. The two methods measure the expansion rate at different epochs. The CMB-derived measurement, from Planck, is measuring the universe as it was approximately 13 billion years ago, shortly after the CMB was released. The distance ladder measurement, using Cepheid variable stars and type 1a supernovae, is measuring the universe as it is today. The Hubble constant, in the standard model, should be the same at both epochs, because the expansion history is fully specified by the model. That it is not the same is the tension, and the direction of the tension is specific. The universe today appears to be expanding faster than it was in the early universe, faster than the standard model predicts given the early universe conditions. One class of explanations says the early universe measurement is wrong. Perhaps the Planck data has a systematic error in the CMB temperature, or the acoustic oscillation scale is being interpreted incorrectly. Independent checks have not found a credible source of error of the required magnitude. Another class says the late universe measurement is wrong. Perhaps Cepheid variables behave differently in different galactic environments, in ways that corrupt the calibration. The 2023 Webb calibration of Cepheids, which should have produced cleaner results than Hubble by resolving individual stars in crowded environments more precisely, did not close the gap. A third class of explanations says both measurements are correct, and the physics connecting the early and late universe is the problem. In between the CMB epoch and today, Lambda CDM predicts a specific expansion history driven by the balance of dark matter, ordinary matter, dark energy, and radiation. If any of those components behaves differently than assumed, the predicted expansion history changes, and the two measurements, which were both correct individually, would disagree, because they were effectively measuring through different physics. This is the class of explanation that the DESI results support. If dark energy has been changing its effective strength across cosmic time rather than maintaining a constant value, then the expansion history between the CMB epoch and today is different from what Lambda CDM assumes, and the Hubble tension becomes not a measurement problem, but a symptom of a physics problem. The dark energy component of the universe is not what we thought it was. The DESI instrument, the Dark Energy Spectroscopic Instrument at the Kitt Peak National Observatory in Arizona, was specifically designed to test whether dark energy is constant or evolving. It works by measuring baryon acoustic oscillations, the characteristic scale of galaxy clustering that originated as sound waves in the early universe plasma. That scale, roughly 490 million light-years in comoving coordinates, acts as a standard ruler. Measure its apparent size at different distances, and you read off the expansion history at different epochs. The DESI survey measured this standard ruler at 10 different distance ranges, corresponding to 10 different periods in cosmic history. If dark energy is a true cosmological constant, the apparent size of the standard ruler, as a function of distance, should follow a specific curve. If dark energy evolves, the curve deviates from the prediction. The DESI results, published in April of 2024, and based on the first year of data from a planned 5-year survey of 40 million galaxies, show a statistically significant preference for a dark energy equation of state that changes with time. The statistical significance is approximately 2 to 3 standard deviations, depending on the data combination used, not yet at the 5 sigma threshold for a definitive claim, but consistent across multiple independent analyses. More data will come. The DESI survey has a planned timeline extending through 2026, and combining the full DESI dataset with data from the Rubin Observatory and Euclid will dramatically increase the statistical power of the test. If the signal is real, the growing dataset will drive the significance upward. If it is a statistical fluctuation or a systematic error, additional data will reduce it. Cosmologists are watching, but notice the accumulation. 4 anomalies, each from a different instrument, each using different techniques, each confirmed by independent analyses. The early galaxy masses from James Webb, confirmed spectroscopically. The early galaxy chemical abundances from James Webb, confirmed spectroscopically. The Hubble tension from both Planck and the distance ladder, confirmed by multiple calibration approaches, and now surviving a Webb recalibration. The dark energy evolution from DESI, consistent across multiple data combinations, and behind all of them, the theoretical problem that there is no successful quantum field theory prediction of the cosmological constant. Consider what it would mean if each of these anomalies had a separate, unrelated explanation within the existing framework. The galaxy masses are due to some unusual initial condition in the early universe not captured by simulations. The chemical abundances are due to some unusual mode of star formation we have not modeled. The Hubble tension is due to some subtle systematic in the Cepheid calibration that even Webb missed. The DESI signal is a statistical fluctuation that will disappear with more data. This is not impossible. Science is full of cases where apparent anomalies dissolved under further examination, but the probabilistic argument cuts against this interpretation. Each explanation invoked for one anomaly needs to be independent of the explanations for the others, and each needs to be plausible on its own. The more anomalies that require separate, independent explanations, the less likely the framework is to be complete. The alternative is that the anomalies share a common root, that something in the foundational assumptions of the standard model is wrong in a way that systematically produces discrepancies across multiple measurement types. This is how physical anomalies have historically behaved when they were signs of something fundamentally new. They were not isolated. They were symptoms of a single, underlying mismatch between the model and reality. The Hubble tension is not the only tension in the cosmological data. There is also the sigma-8 tension, a discrepancy between the predicted and observed clumping of matter on intermediate scales. The standard model, using CMB-derived parameters, predicts a specific level of matter clustering in the universe today. Measurements of the weak gravitational lensing of galaxies, which provides an independent probe of matter clustering, consistently produce a value slightly lower than predicted. The discrepancy is at the 2 to 3 sigma level, statistically less severe than the Hubble tension, but present and consistent across multiple lensing surveys. The sigma-8 tension could have the same root as the Hubble tension if dark matter has properties slightly different from the cold, non-interacting particles assumed in the standard model. Warm dark matter, in which the dark matter particles have a small but non-zero initial velocity, suppresses small-scale structure formation in a way that could partially reconcile the lensing measurements with the CMB predictions. But warm dark matter adjustments that reduce sigma-8 to match lensing observations also change other quantities that are currently measured to agree with the standard model, creating new tensions elsewhere. This is the pattern. Every proposed internal fix to the standard model that addresses one anomaly creates pressure somewhere else. The framework is not rigid in the sense of refusing to accommodate any modification. It is rigid in the sense that the modifications that would be needed to close all the tensions simultaneously appear to be mutually incompatible. The model can be bent to fit one anomaly. Bending it to fit 4 simultaneously seems to require bending it in directions that break it in other ways. One of the most important recent developments in the theoretical effort to understand these tensions is the recognition that the Hubble tension is not just a number. It has a shape. The two methods disagree not just in the value they produce for the expansion rate, but in a way that encodes information about what kind of new physics, if any, could resolve the discrepancy. Early dark energy is the most thoroughly investigated proposed resolution. The idea is that there was a brief period, very early in the universe's history, when dark energy was not at its present extremely small value, but was significantly larger. This extra energy density in the early universe would have caused space to expand slightly faster than standard model predictions, reducing the sound horizon, the scale over which sound waves traveled before recombination, and therefore changing the CMB predicted Hubble constant upward toward the distance ladder value. The problem with early dark energy is that it does not just change the Hubble constant, it changes the entire acoustic oscillation structure of the CMB in a way that is constrained by the data. Planck measured the acoustic peaks of the CMB to extraordinary precision across multiple harmonics. The shape of those peaks constrains the early dark energy quite tightly. Models that push the Hubble constant up enough to close the tension tend to produce acoustic peak shapes that disagree with the measured ones in other ways. There are fine-tuned versions that nearly work, but the parameter space that resolves the Hubble tension while preserving everything else the standard model gets right is very narrow, and the fine-tuning required is itself a theoretical problem. This situation is familiar from the history of particle physics. The standard model of particle physics has its own fine-tuning problems, most notably the hierarchy problem. The Higgs boson mass is extremely small compared to the Planck scale, and keeping it small requires extraordinary cancellations between very large numbers, a situation that suggests the Standard Model is an effective description, valid only up to some energy scale, where new physics intervenes. The proposed solutions to the hierarchy problem, supersymmetry and extra dimensions being the most prominent, predicted new particles that should have appeared at the energies probed by the Large Hadron Collider. They have not appeared. The hierarchy problem remains unsolved, and the solutions proposed for it are increasingly constrained. The situation in cosmology rhymes with the situation in particle physics. In both cases, the Standard Model works. In both cases, there are things the Standard Model cannot explain. The fine-tuning of the constants, the hierarchy problem, the nature of dark matter, the nature of dark energy, the origin of the matter-antimatter asymmetry that allowed the universe to exist rather than annihilating itself in the first instant. In both cases, the proposed extensions of the Standard Model have not been confirmed by experiment. And in both cases, the discrepancies that have appeared, when they have appeared, have come from precisely the measurements that probe the model at its limits. The matter-antimatter asymmetry deserves a moment of attention because it is one of the most basic unsolved problems in physics, and it is a problem that is directly connected to the existence of everything. In the Standard Model of particle physics, the laws of physics should treat matter and antimatter symmetrically. When matter is created from energy, an equal amount of antimatter should be created simultaneously. When matter and antimatter meet, they annihilate, converting back to energy. If the early universe produced equal amounts of matter and antimatter, they should have annihilated each other completely, leaving a universe filled with radiation and nothing else. No stars, no galaxies, no planets, no observers. The universe we live in contains matter. The mechanism by which matter came to predominate over antimatter is called baryogenesis, and it is not explained by the Standard Model of particle physics. The Standard Model contains a small amount of matter-antimatter asymmetry from a process called CP violation, but not nearly enough to account for the observed predominance of matter. There must be additional sources of CP violation not yet observed, or the matter-antimatter asymmetry arose through a mechanism not yet identified. This is not directly connected to the anomalies James Webb is observing, but it belongs in any honest accounting of what the Standard Models, both the cosmological and the particle physics versions, leave unexplained. The universe we live in exists because something violated the symmetry between matter and antimatter in the early universe. We do not know what that something was. What we can trace is the path from the Big Bang to the complexity observable today, and note where the Standard Models fit well and where they do not. In the first second after the Big Bang, physics was operating at energies far above anything accessible to current particle accelerators. The Standard Model of particle physics is believed to be accurate only at energies below its natural scale, and the early universe briefly exceeded that scale. What happened above that scale is governed by physics we do not have a confirmed theory for. The standard cosmological model effectively treats this period as an initial condition, starting with the universe, at the moment when energies drop to accessible ranges, and assuming the state at that moment was, as the CMB observations indicate. From that moment, the physics is relatively well constrained. The universe was a hot plasma of quarks, gluons, photons, neutrinos, electrons, and other particles. As it expanded and cooled, quarks combined into protons and neutrons. Protons and neutrons combined into the light nuclei, hydrogen, deuterium, helium, and small amounts of lithium. This process, called Big Bang nucleosynthesis, is one of the Standard Model's most precise successes. The predicted abundances of hydrogen and helium match observations of the oldest, most pristine gas clouds in the universe to better than 1%. This is a strong confirmation that the Standard Model describes the physics of the universe correctly at that epoch, roughly 10 seconds to 20 minutes after the Big Bang. After nucleosynthesis, the universe continued cooling for roughly 380,000 years, until the temperature dropped enough for electrons to bind to nuclei, forming neutral hydrogen. At this moment, the universe became transparent to light for the first time, releasing the CMB. The pattern of temperature fluctuations in the CMB encodes the distribution of matter density at that moment, a snapshot of the seeds from which all subsequent structure grew. For the next several hundred million years, the universe was dark. There were no stars, there were no galaxies, only slowly deepening overdensities in the distribution of dark matter and gas, drawn together by gravity in the long, patient process of structure formation. This period is called the cosmic dark ages. And one of the observational goals of James Webb and future radio telescopes is to detect the signal from the end of this period, the moment when the first stars ignited and began reionizing the surrounding gas. The first stars are believed to have been very different from the stars that exist today. They formed from gas that contained only hydrogen and helium, with no heavier elements to radiate away heat efficiently. This limited the ability of the gas to cool and fragment, producing stars that were significantly more massive than typical stars today, some potentially hundreds of times the mass of the Sun. These are called population 3 stars, and they have never been directly observed. Their existence is inferred from theory and from the pattern of chemical abundances in the oldest stars that can be observed. Population 3 stars would have burned through their fuel quickly, in millions rather than billions of years, and died in spectacular supernovae that scattered the first heavy elements into the surrounding gas. The chemical enrichment of the universe began with these deaths. The gas enriched by population 3 supernovae collapsed to form the next generation of stars, slightly richer in metals, and so on in a cascade that produced the diversity of stellar chemistry observable today. This cascade takes time, and it is the time requirement that James Webb's observations are challenging. The DESI survey's detection of evolving dark energy adds another dimension to this picture. If the vacuum energy is not constant but has been evolving throughout cosmic history, then the expansion history of the universe is different from what the standard model assumes. The expansion rate determines how fast structure can form. A faster expansion rate suppresses structure formation by stretching space faster than gravity can pull matter together. A slower expansion rate allows more time for structures to deepen. If the dark energy was stronger in the past than assumed and has been weakening, or if it was weaker in the past and has been strengthening, the timeline of structure formation needs to be recalculated. This has implications not just for the early universe anomalies, but for the entire history of cosmic evolution. The growth of galaxy clusters, the formation of large-scale filaments, the distribution of matter at different redshifts, all of these are sensitive to the expansion history in ways that could distinguish between different dark energy models if the data are precise enough. The full DESI survey, combined with the Rubin Observatory's legacy survey of space and time scheduled to begin producing science data in the mid-2020s, will probe these signatures with unprecedented precision. There is also the question of what dark matter actually is. Lambda CDM treats dark matter as a cold, non-relativistic, weakly interacting substance whose only significant interaction is gravitational. This description works remarkably well at large scales. Galaxy rotation curves, the evidence that first convinced astronomers dark matter must exist, show that the orbital velocities of stars and gas in galaxies stay flat at large radii, rather than falling off, as they would if all the mass were concentrated in the visible disk. The flat rotation curves are consistent with a halo of dark matter extending far beyond the visible galaxy. The bullet cluster provides arguably the most direct evidence for dark matter. When two galaxy clusters collided, the hot intergalactic gas, which is visible in X-rays, was slowed by the electromagnetic drag of the collision and lagged behind the galaxies themselves. The total mass distribution of the merge system, measured through gravitational lensing, shows two peaks separated from the X-ray emission. The mass is not where the gas is. The mass moved through the collision with the galaxies, without interacting electromagnetically, exactly as weakly interacting dark matter would behave. This observation strongly constrains alternatives to dark matter that attempt to explain galaxy dynamics by modifying gravity, because in the bullet cluster geometry, modified gravity cannot easily explain the offset between the X-ray gas and the gravitational mass. Yet despite decades of experimental effort, no direct detection of dark matter particles has been achieved. The WIMP, for weakly interacting massive particle, was for 2 decades the most theoretically motivated dark matter candidate. WIMPs arise naturally in supersymmetric extensions of the standard model of particle physics. They would have been produced in the right abundance in the early universe for the observed dark matter density, and they would be detectable through rare collisions with ordinary nuclei in sensitive underground detectors. Experiments including LUX, Xenon, and LZ have probed the WIMP parameter space to extraordinary depths without detecting a signal. The most theoretically natural part of the WIMP parameter space is now largely excluded. This does not mean dark matter does not exist, or even that WIMPs do not exist. There are corners of the parameter space not yet probed. There are other dark matter candidates: axions, sterile neutrinos, primordial black holes, ultralight dark matter fields. Each has its own experimental signatures and its own theoretical motivations. But the failure to detect the most predicted candidate after decades of sensitive searching is itself informative. Either dark matter is something more exotic than the simplest models predicted, or the modifications to gravity proposed by Milgram and others, which have had modest observational success at galactic scales but struggle with clusters, deserve more serious theoretical development. What connects all of these threads is that there are questions about the nature of 80% of the matter in the universe and 68% of the total energy content. Lambda CDM works because it incorporates these components with the right overall abundances. It does not explain what they are. Dark matter and dark energy are names for measured quantities without identified physical causes. The standard model of cosmology is, in this sense, a framework with two major unknown ingredients. Fred Hoyle's carbon resonance calculation is worth returning to in this context because it illustrates something profound about how physics constrains itself. The carbon-12 nuclear resonance is not predicted by quantum chromodynamics from first principles. It happens to exist at a value that allows stellar nucleosynthesis to proceed at a rate consistent with the observed abundance of carbon. Hoyle's argument that it must exist because we exist is compelling logic, but it is not a derivation of the resonance from underlying physics. The resonance is empirically real. The reason its energy level sits where it does, rather than at a slightly different value that would make carbon rare or absent, is not explained by the standard model of particle physics. This is one instance of the broader fine-tuning problem. The 26 constants of physics are not derived from any currently known first principle. They are measured. The question of why they have the values they do is not answered by any current theory. Three categories of answer have been proposed. Anthropic selection in a multiverse, where only the subset of universes with life-permitting constants contain observers to measure them. A deeper theory that will eventually derive the constants as mathematical necessities from some higher-order structure, or just the brute fact that they have these values, with no further explanation available. The multiverse answer has the virtue of being connected to physics that cosmologists accept for independent reasons, namely eternal inflation. But it has the vice of being in principle unverifiable. If the other universes can never be observed, the claim that they exist can never be tested. Some physicists consider this a fatal flaw. Others argue that unverifiability does not make a claim wrong, and that a theory with good explanatory power and a connection to well-tested physics is worth taking seriously, even if it cannot be directly confirmed. The deeper theory answer is the one that physicists would most prefer, because it would retain the connection between physics and experiment. If the constants can be derived from first principles, those first principles could in principle be tested. String theory was the most ambitious attempt to provide such a framework. It succeeded in producing a consistent mathematical description of quantum gravity, the long-sought unification of quantum mechanics and general relativity. It failed, so far, to produce a unique prediction of any particular constants. The landscape of 10 to the power of 500 possible configurations means that string theory, as currently understood, is consistent with almost any values of the constants. This makes it difficult to test and harder to trust as the kind of fundamental derivation that would explain why the constants are what they are. Lee Smolin proposed an interesting variation in 1992 called cosmological natural selection. In his model, black holes give birth to new universes, with the constants of the daughter universes slightly different from the parent. Universes that produce more black holes produce more descendants. Natural selection favors whatever constants maximize black hole production. Our universe happens to sit near a peak of black hole productivity in the landscape, which is why our constants allow the formation of massive stars that produce black holes. And as a side effect of constants that allow massive stars, those same constants allow the full range of stellar evolution, including the nucleosynthesis of heavy elements and the formation of chemistry complex enough to support life. This proposal has an interesting feature that the standard multiverse argument lacks. It makes testable predictions. Specifically, it predicts that our constants should be near a local maximum of black hole production rate, meaning that any small change in the constants should reduce the number of black holes. Several physicists have examined whether this prediction holds and found that some constants satisfy it and others do not. The status of the prediction is contested, but the framework is notable for being a version of the multiverse argument that is not entirely immune to empirical scrutiny. The question of what comes after lambda CDM is not only about replacing the model, it is about what kind of replacement is possible. The history of physics suggests that the replacement will need to reduce to lambda CDM in the situations where lambda CDM works well, which is most of the observable universe at most of the observable times, while predicting the anomalies that lambda CDM cannot accommodate. This is the same structure as the relationship between general relativity and Newtonian mechanics. General relativity reduces to Newtonian mechanics in the limit of weak gravitational fields and slow velocities. Mercury's 43 arcseconds per century is one of the places where that limit breaks down. What are the anomalies that a successful replacement model needs to predict? The list is specific and measurable. Massive galaxies at high redshift with stellar masses exceeding the standard model budget. Chemical abundances in early universe galaxies that require stellar generations the standard timeline has no room for. An expansion rate today 9% higher than the CMB-derived value, with neither measurement having a known systematic error of the required magnitude. Dark energy that shows a preference for dynamical evolution rather than a constant value. A structure on scales of 10 billion light-years that exceeds the homogeneity scale required by the cosmological principle. And underlying all of them, a vacuum energy that quantum field theory predicts should be 120 orders of magnitude larger than observed. A theory that predicts all of these, while preserving the successes of lambda CDM in the CMB power spectrum, baryon acoustic oscillations, Big Bang nucleosynthesis, and the abundance and distribution of galaxy clusters, would be extraordinary. No current candidate theory does this. The search is active. What research groups around the world are doing is not working toward a single pre-announced goal, but exploring multiple directions simultaneously, testing each against the growing dataset, and looking for signatures that would distinguish between models. This is how physics has always worked at the frontier. The next generation of surveys, including the full DESI dataset, the Euclid Wide Field Imaging Survey, the Rubin Observatory's decade-long survey of the southern sky, the Square Kilometer Array's radio survey of hydrogen across cosmic history, and continued observations from James Webb, will collectively produce a dataset far richer than anything available today. If a new physics is responsible for the anomalies, that physics should leave signatures across multiple datasets. A dark energy that evolves should affect not just the expansion rate, but the growth of structure in a correlated way. Early dark energy should leave specific imprints on the CMB beyond the Hubble constant shift. Modified gravity should predict different clustering statistics than dark matter. Each of these discriminating tests can be made with the data that is already being collected. The possibility that the resolution involves not new physics within the existing mathematical framework, but a new mathematical framework, is harder to test by definition. If space is not fundamental but emergent, the right starting point for cosmology might not be general relativity on a space-time manifold, but some more basic structure from which space-time, matter, and the laws connecting them all emerge together. This is the direction that ADS, CFT, and the holographic principle point. The mathematics of that direction is being actively developed, but it has not yet produced a complete cosmological model that can be compared against observation with the precision that lambda CDM can. The situation is genuinely open. The anomalies are real, the framework is strained, the replacement has not arrived. This is an uncomfortable position for a field that spent 30 years in the productive confidence that the model was working. But it is also the most scientifically interesting position. The frontier of cosmology is not at the level of refining confirmed predictions. It is at the level of identifying the failure modes of the best available model and searching for the physics that explains them. John Mather's 4 words, "This is not our universe," are most accurately understood not as a statement of defeat, but as a statement of precision. The standard model was built from measurements taken inside a particular region of space-time during a particular epoch of cosmic history. The model worked in that region and at that epoch with extraordinary fidelity. What the James Webb Space Telescope has done is extend those measurements further back in time than any previous instrument could reach, and at that greater reach, found conditions the model did not predict. The universe Mather helped to describe in the 1980s and 90s was the universe visible to the instruments of that era. The universe Webb is revealing is the same universe, seen in regions and at times that were previously inaccessible. That the model built from the restricted view does not fully describe the extended view is precisely what you would expect if the model was accurate within its domain and was being applied beyond it. The question now is what extended model describes not just the subset of the universe accessible to Planck and the CMB satellites, but the full range of cosmic history back to the formation of the first structures and the conditions that determined the constants. That question does not yet have an answer. The instruments to gather the data needed to constrain the answer are already operating or in development. The theorists working to construct possible answers are doing so against a background of anomalies that any successful theory must predict from first principles, not accommodate after the fact. The telescope is still running, the data is still arriving, and the picture it is building is not the picture of the universe the models predicted. It is something more complex, more constrained by observation, and ultimately more interesting. The gap between the standard model and the observations is not a failure of science. It is science working correctly, extending its reach until the model can no longer accommodate what is found, and preparing the ground for whatever comes next. Whatever comes next will need to explain why 6 massive galaxies existed 500 million years after the Big Bang fully formed and chemically enriched. It will need to explain why the expansion rate today is 9% higher than the early universe conditions predict. Sure. It will need to explain why dark energy appears to evolve rather than sit fixed. It will need to explain why the largest observed structures exceed the homogeneity scale the cosmological principle requires. And it will need to connect all of this to a description of the vacuum energy that does not differ from the quantum field theory prediction by 120 orders of magnitude. These are not small problems. They are the problems that define the frontier of physics in the current era. The instruments to probe them are operating. The data is accumulating. The answer is not yet here. But the shape of the question is becoming, with each new observation, more precisely defined. And that precision is exactly what you want before you start looking for the answer. To fully appreciate what is at stake in the current confrontation between observations and the standard model, it helps to understand the mathematical structure that lambda CDM is built on, and why departures from it are so consequential. The cosmological principle, the assumption that the universe is homogeneous and isotropic at the largest scales, is not an observational conclusion. It is a mathematical prerequisite that makes the equations tractable. The field equations of general relativity are enormously complex in their full form. In a universe with arbitrary matter distribution, solving them for the evolution of every point in space simultaneously is computationally impossible even in principle. The cosmological principle reduces this problem to a manageable one. If the universe looks the same everywhere, and in every direction at the largest scales, then the geometry of space itself can be described by a single function of time, the scale factor, which tells you how the distance between any two fixed points changes as the universe evolves. Everything follows from this function. The metric that results from applying the cosmological principle to general relativity is called the Friedmann-Lemaitre-Robertson-Walker metric, usually abbreviated FLRW. It is the mathematical backbone of all of modern cosmology. From it, the equations of motion for the scale factor can be derived, and those equations, called the Friedmann equations, connect the expansion rate to the total energy density. Dark matter, ordinary matter, radiation, and dark energy each contribute to the total energy density with different dependencies on the scale factor, and together they determine how the universe has expanded from the Big Bang to today, and how it will expand in the future. The cosmological principle itself is tested observationally through the large-scale distribution of galaxies. The assumption is that above some characteristic scale, the universe smooths out into a statistically uniform distribution. The scale at which this happens is estimated to be roughly 300 million light-years, based on galaxy survey data. Below that scale, matter is organized into the complex cosmic web of filaments, voids, sheets, and clusters that characterizes the universe at observable scales. Above it, the distribution should approach uniformity. The Hercules Corona Borealis Great Wall violates this picture. It is a concentration of galaxy clusters spanning approximately 10 billion light-years, detected through the spatial distribution of gamma-ray bursts, which serve as tracers of the underlying mass distribution. 10 billion light-years is 30 times the scale above which the universe is supposed to be homogeneous. A structure this large should not exist if the cosmological principle is correct. The response within the research community has been cautious. Gamma-ray burst distributions are subject to observational biases, and the statistical analysis required to establish the significance of the Great Wall's overdensity is complex. But the structure has not gone away with additional data, and its theoretical implications are severe enough that serious researchers have begun examining what it would mean if the cosmological principle is not a good description of the universe at the scales probed by the largest surveys. If the cosmological principle fails at 10 billion light-year scales, the FLRW metric does not accurately describe the universe at those scales. And if the metric is wrong, every quantity derived from it, including the Hubble constant, the age of the universe, the distance to the CMB surface, and the predictions for baryon acoustic oscillations, needs to be recalculated in the context of the correct metric. This is not a small correction. It is a fundamental revision of the mathematical framework. The possibility that we live in a universe with large-scale inhomogeneity was explored, theoretically, in the 1990s and 2000s, in the context of explaining the apparent accelerated expansion without dark energy. The idea was that if the Milky Way sits near the center of a large void, the local expansion rate could appear faster than the global average, mimicking the effect of dark energy without requiring vacuum energy. These models were eventually constrained by observations that showed the CMB temperature distribution is inconsistent with being at the center of a very large void, but they illustrate the sensitivity of cosmological conclusions to assumptions about large-scale structure. The discovery of dark energy itself in 1998, through observations of Type 1, a supernovae at high redshift, is worth revisiting in this context. Two independent teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were using supernovae as standard candles to measure the expansion history of the universe. The supernovae at high redshift appeared fainter than expected for a universe decelerating under its own gravity. They were further away than they should have been. The conclusion was that the expansion was not decelerating, but accelerating, driven by some form of energy with negative pressure that was pushing space apart. This was dark energy. Both teams shared the Nobel Prize in Physics in 2011. Type 1a supernovae became the foundational measurement of the distance ladder at cosmological scales, and they remain so today. Understanding their systematic uncertainties is therefore central to understanding the Hubble tension. Type 1a supernovae are believed to be the result of a white dwarf accumulating mass from a companion star until it reaches a critical mass and explodes in a thermonuclear detonation. Because the explosion always occurs at approximately the same mass, the intrinsic brightness should be approximately the same for every such event, making them reliable standard candles after a calibration correction based on the shape of their light curve. The precision of this calibration has been the subject of intensive research for 2 decades. The calibration depends first on tying Type 1a supernova distances to Cepheid variable star distances, and Cepheid distances, in turn, depend on distances to the galaxies containing them measured through geometric parallax or other fundamental methods. Each link in this chain introduces potential systematic errors that accumulate. The Webb Space Telescope's recalibration of the Cepheid distance ladder, completed in 2023, was specifically designed to address one of the most commonly cited potential systematic errors: crowding. In dense stellar environments, the light from multiple stars blends together in a way that can affect the apparent brightness of individual Cepheids and corrupt the calibration. Webb's superior angular resolution can separate sources in crowded fields that appeared blended in Hubble images. The result of applying this cleaner calibration was a Hubble constant measurement from the distance ladder that remained at 73 kilometers per second per megaparsec, essentially unchanged from pre-Webb measurements. The calibration got better, and the gap did not close. This is one of the strongest pieces of evidence that the Hubble tension is not a calibration artifact. The most obvious potential source of systematic error in the distance ladder has been specifically tested with a better instrument and found not to be the problem. Whatever is causing the 9% discrepancy is either a more subtle, systematic, that both Hubble and Webb measurements share, which would need to be identified and quantified before being invoked as an explanation, or it is a real physical difference in the expansion rate between the early and late universe. The possibility that both measurements are correct and the physics is the problem has increasingly taken center stage in theoretical discussions. If the universe expanded differently in the past than the standard model assumes, both the CMB-derived and distance ladder-derived Hubble constants could be accurate measurements of what they claim to measure, and they could disagree because they are effectively measuring through different epochs of physics. One proposed mechanism involves interactions between dark matter and dark energy. In the standard model, dark matter and dark energy are independent components that do not interact with each other. They are both present, they both contribute to the expansion, but one does not affect the other. If instead there is a flow of energy between the dark sector components, the expansion history of the universe changes in ways that can shift the CMB-derived Hubble constant. Models with dark sector interactions can, in some parameter ranges, reduce the Hubble tension. They also introduce new predictions for the large-scale structure of the universe that can be tested against galaxy surveys. Another class of models involves modifications to the neutrino sector. Neutrinos are the lightest known massive particles, produced copiously in the early universe and still present today as a cosmic background. The mass of neutrinos affects structure formation and, through the early universe thermal history, the CMB acoustic oscillation scale. Measurements of neutrino masses from laboratory experiments are consistent with the cosmological bounds, but the upper limits on neutrino masses from cosmology are sensitive to the assumed cosmological model. If the standard model is wrong, in a way that affects the inferred neutrino mass bound, the neutrino contribution to the early universe energy density would be different from assumed, and the CMB-derived Hubble constant would shift. None of these proposals have yet closed the Hubble tension, while preserving all the other successes of the standard model. Each is being tested against the growing dataset. Each represents a possible signal of new physics that might be real or might not be. The data is the arbiter. The interplay between the Hubble tension, the early galaxy problem, and the DESI dark energy results is particularly interesting when examined together. If dark energy has been evolving across cosmic history, the expansion rate at different epochs is different from the standard model prediction. A dark energy that was stronger in the past than today would have caused faster expansion in the intermediate universe, which could push the distance ladder-derived Hubble constant higher than the CMB-derived value. The direction of the required dark energy evolution in this scenario is broadly consistent with what the DESI data is beginning to indicate. This is not a proof that the anomalies share a common root, but it is a consistency check that suggests they might. The early galaxy problem sits somewhat separately. Dark energy evolution primarily affects the expansion rate, and therefore the available time for structure to form at different epochs. But the galaxy masses Webb is finding are so extreme that even a modified expansion history is unlikely to fully accommodate them without also changing the primordial density fluctuation spectrum or the efficiency of structure formation in more fundamental ways. The early galaxy problem may require physics that operates at shorter scales, within the galaxies themselves, rather than at cosmological scales. This is where population 3 stars and the first generation of stellar evolution become important. If the first stars were significantly more massive than currently assumed, they would have lived shorter lives, died more violently, enriched the surrounding medium with heavy elements more rapidly, and provided more radiation for ionizing the surrounding gas. All of these effects would accelerate the early evolution of galaxies. Population 3 stars are a consequence of the simple initial chemical composition of the universe and the resulting opacity of the first gas clouds to radiation, which limited their ability to fragment into smaller, lower-mass stars. The theory predicts they should have been massive. The question is whether they were massive enough to account for the James Webb observations, and whether the standard model of their formation is correct. One possibility that researchers are actively investigating is that the first stars had a top-heavy initial mass function, meaning they were not just more massive on average than stars today, but that the population was dominated by the very most massive objects. A population in which many stars had masses of several hundred solar masses or more would produce supernovae so energetic that they could enrich large volumes of gas very quickly, explaining the rapid chemical enrichment James Webb is detecting. These pair instability supernovae, which occur when the most massive stars become unstable to electron-positron pair production in their cores, are predicted by physics and have been tentatively identified in a small number of observed supernovae in the local universe. Whether they were common in the early universe is something James Webb observations of chemical abundance patterns may be able to constrain. The DESI results on dark energy evolution are themselves part of a broader effort to map the expansion history of the universe using multiple independent probes. Baryon acoustic oscillations are the cleanest probe because they are measured from the clustering statistics of millions of galaxies and are relatively immune to astrophysical systematic effects. The scale of the acoustic oscillations is set by the sound horizon at recombination, the distance that sound waves traveled in the early universe plasma before the CMB was released. This scale is precisely measured from the CMB. When the same scale is detected in the three-dimensional distribution of galaxies at various redshifts, the ratio of the observed scale to the CMB measured scale gives the expansion factor between the CMB epoch and the galaxy observation epoch. Repeat this measurement at many redshifts, and you reconstruct the full expansion history. The DESI team also uses quasar spectra to probe the three-dimensional hydrogen gas distribution at even higher redshifts than galaxies through a technique called the Lyman alpha forest. Quasars are the bright active nuclei of distant galaxies, powered by matter falling into supermassive black holes. Their light passes through intervening gas, which absorbs it at specific wavelengths corresponding to the hydrogen-Lyman alpha transition at the redshift of the absorbing gas. The pattern of absorption features encodes the distribution of hydrogen gas along the line of sight, which traces the large-scale structure of the universe at high redshift. The Lyman alpha force measurements from DESI will extend the baryon acoustic oscillation probe back to redshifts of 2 and beyond, probing the expansion history in the epoch when dark energy was less dominant than matter. Combining all of these probes, the DESI team will be able to map the dark energy equation of state, the ratio of its pressure to its energy density, as a function of redshift with precision that was not available from any previous survey. The equation of state of a cosmological constant is exactly -1, meaning its pressure is equal and opposite to its energy density, which is what drives the accelerated expansion. A dark energy that departs from this value is dynamical, and the pattern of its variation with redshift carries information about its physical nature. Models of dynamical dark energy include quintessence, a slowly rolling scalar field whose energy density changes over time; quiescence, a scalar field with a non-standard kinetic term; coupled dark energy, where the scalar field interacts with dark matter; and many others. Each predicts a specific pattern of dark energy evolution as a function of redshift. The DESI data will constrain which patterns are consistent with observation and which are not, narrowing the theoretical space significantly. The observation that sits uncomfortably alongside all of these dynamical dark energy models is the vacuum catastrophe. If dark energy is a dynamical scalar field, rather than the energy density of the quantum vacuum, the fine-tuning problem might be reframed. The cosmological constant problem, in its original form, is the problem of why the quantum vacuum energy density is so much smaller than quantum field theory predicts. If dark energy is not the vacuum energy density, but a separate dynamical field, you still need to explain why the vacuum energy is small, but you now have a dynamical field whose current energy density can in principle be set by initial conditions or by some attractor mechanism, rather than requiring a precise cancellation between large terms. This is not a solution to the vacuum catastrophe, but it is a possible reformulation. If dark energy is quintessence, the vacuum energy problem and the dark energy problem are separate problems. Some physicists consider this better than having one enormous unsolved problem, while others point out that introducing a dynamical scalar field, fine-tuned to have a very small energy density today, simply moves the fine-tuning from one place to another. The question of what dark energy is, at the fundamental level, is connected to the question of what the universe's current accelerated expansion actually signifies. In the 1990s, before the supernova observations confirmed acceleration, most cosmologists assumed the universe was decelerating under its own gravity, moving toward eventual collapse, or, at best, ever-slowing expansion. The discovery of acceleration changed the long-term fate of the universe fundamentally. In an accelerating universe, the expansion eventually outpaces the ability of gravity to hold structures together. Galaxies beyond a certain distance recede faster than light can return from them and become permanently inaccessible. On extremely long timescales, the observable universe shrinks as previously accessible galaxies cross the horizon. On even longer timescales, if the acceleration continues, the heat death scenario unfolds. Individual galaxy groups remain gravitationally bound and continue to evolve, but they are islands in an increasingly empty universe. Stars exhaust their fuel, black holes form and eventually evaporate through Hawking radiation. The temperature approaches absolute zero. Entropy reaches its maximum. Time continues, but nothing changes. This is the thermodynamic fate of an eternally accelerating universe. But if dark energy evolves, as the DESI data suggests, this picture changes. The evolution of dark energy over the next trillion years, or the next 100 trillion years, is not something DESI or any other current instrument can measure directly. We are observing dark energy over a few billion years of cosmic history, a small fraction of the universe's total past, let alone its future. Extrapolating from a few billion years of measured evolution to trillions of years of future evolution requires assuming that the underlying physics of dark energy does not change in ways not captured by the current measurements. This is a limit of observation that physics cannot currently overcome. The fate of the universe is constrained, but not determined, by what we can measure. The DESI results reduce the certainty with which any particular ending can be predicted, not because they make the future uncertain in a new way, but because they reduce the certainty that the cosmological constant is truly constant, and a constant that is not constant changes every calculation built on the assumption that it is. What remains most striking across all of these anomalies and all of these open questions is the scale of what is unknown compared to what is known. The standard model of cosmology describes 5% of the universe with excellent precision. It names, but does not explain 95% of the universe. The 5% it describes in detail is everything that can be seen, every star, every galaxy, every atom of ordinary matter. The 95% it cannot identify is dark matter and dark energy, invisible to every telescope, inferred only through their gravitational and expansionary effects on the 5% that is visible. When physicists describe the standard model as highly successful, they are describing a framework that explains the distribution, clustering, and evolution of 5% of the universe's content with remarkable precision, while using named placeholders for the other 95%. This is not a criticism. The alternative, ignoring the gravitational and expansionary effects of the invisible components, produces predictions that disagree with observation far more severely. The framework works because it incorporates the effects of dark matter and dark energy with the right magnitudes, even if it cannot identify their origins. But this means the foundational questions about the universe, what most of it is made of, and why it is expanding the way it is, remain open. James Webb's observations are pushing on the edges of the model that accommodates these open questions. The anomalies it is finding are not in the well-understood 5%. They are in the behavior and history of the structures that formed from that 5% under the influence of the 95% we cannot see. Every anomaly in early galaxy formation is also an anomaly in the behavior of dark matter halos and dark energy at high redshift. Every anomaly in the expansion rate is an anomaly in the evolution of the invisible components. To resolve the anomalies, we need to understand not just what dark matter and dark energy are, but how they behave at epochs and scales that current observations are only beginning to probe. This is why the combination of James Webb, DESI, Euclid, and the Rubin Observatory represents such a scientifically important observational program. Each instrument probes different aspects of the same underlying physics from different directions. Where their results converge, confidence increases. Where they diverge from the standard model, the opportunity to identify new physics grows. The researchers doing this work are not working in the shadow of imminent resolution. They are working in the genuine uncertainty of a field that has found its limits and is carefully, systematically extending its reach. The next decade will not produce a new standard model of cosmology complete enough to replace lambda CDM in all its applications. But it may well identify which of the current anomalies are most robust and most constraining, narrowing the theoretical space enough to make the contours of the replacement visible even before the replacement itself arrives. John Mather's 4 words carry weight not because they are alarming, but because they are precise. This is not our universe does not mean the universe is hostile or alien or beyond understanding. It means the universe we described from within our limited observational reach, and then extended to everything, is revealing itself to be more complex and more extensive than the description captured. The description was not wrong, it was local, and the instrument powerful enough to reveal the discrepancy is now running, returning data every day, extending the reach further with every observation. That extension is science working exactly as it should. The standard model is the best summary of what we knew before Webb. The anomalies are the fingerprints of what we did not yet know. The work now is to follow those fingerprints to whatever they lead to, with the same precision and the same commitment to following the data wherever it goes that produced the standard model in the first place. The universe does not owe us a model that fits within our current mathematical vocabulary, but it is telling us, clearly and consistently, where our current vocabulary falls short. That is the starting point for every expansion of understanding that physics has ever achieved. And the telescope is still looking. The story of how physics has repeatedly been forced to revise its deepest assumptions is worth tracing more carefully, because the pattern is informative about what to expect now. Each major revolution in physics followed a similar structure. An anomaly that resisted explanation within the current framework. A period of increasingly strained accommodations, and then a conceptual leap that redefined the framework itself. In the late 19th century, the dominant theory of light held that it was a wave propagating through a medium called the luminiferous ether, the way sound waves propagate through air. The existence of the ether seemed to be required by physics, as then understood. A wave needs something to wave in. In 1887, Albert Michelson and Edward Morley conducted an extraordinarily precise experiment designed to detect the Earth's motion through the ether by measuring slight differences in the speed of light in different directions. Light traveling in the direction of Earth's motion should travel at a slightly different speed than light traveling perpendicular to it. The same way a swimmer moves at different speeds relative to the riverbank, depending on whether they are swimming with, against, or across the current. The experiment found no difference. The speed of light was the same in every direction, regardless of the Earth's motion through space. This result was considered an experimental failure at the time because it failed to detect what it was designed to detect. But the result was real and reproducible. The ether did not appear to exist. For nearly 20 years, physicists attempted to explain the null result within the ether framework. Various proposals were offered, including the idea that matter contracts in the direction of motion in a way that exactly cancels the expected difference, a hypothesis that turned out to be correct, but for reasons that nobody in the ether framework could have guessed. The resolution required abandoning the ether entirely and reconceiving the nature of space and time. Albert Einstein's special theory of relativity, published in 1905, replaced the ether with a new postulate. The speed of light is the same for all observers in uniform motion, regardless of the motion of the source. From this postulate, the contraction of space and dilation of time that physicists had been trying to explain as ether effects emerged as necessary mathematical consequences. The cost of explaining the Michelson-Morley result was Newtonian absolute space and time. The gain was a consistent framework for understanding everything moving at relativistic speeds. The ultraviolet catastrophe of the late 19th century was a different kind of anomaly. Classical physics predicted that a black body, an idealized object that absorbs all incident radiation and re-emits it based solely on its temperature, should emit more and more radiation at higher and higher frequencies, diverging to infinity at ultraviolet and shorter wavelengths. This was clearly wrong. Black bodies emit a finite total amount of radiation following a specific curve that peaks at a wavelength determined by temperature. The classical prediction was not slightly wrong. It was infinitely wrong at high frequencies, a catastrophic failure of the theory. Max Planck found a mathematical formula that fit the observed black body curve exactly, but it required assuming that the oscillators responsible for emission could only absorb and emit energy in discrete packets proportional to the frequency of radiation, packets he called quanta. Planck himself was uncomfortable with this assumption, treating it as a mathematical convenience rather than a physical fact. Einstein took the quantum hypothesis seriously and applied it to explain the photoelectric effect, showing that light itself behaves as if composed of discrete packets of energy, now called photons. This was the beginning of quantum mechanics. The resolution required abandoning the assumption that energy is continuously variable. The gain was a framework for understanding the behavior of matter and energy at the smallest scales, a framework that eventually produced quantum field theory, semiconductor physics, laser technology, and the entire technological infrastructure of the modern world. In each case, the anomaly was not at the edges of the theory. It was in a central, well-tested prediction. The ether should have been detectable, because electromagnetism, one of the most successful theories of the 19th century, required it. The black body spectrum should have diverged, because thermodynamics and electromagnetism together predicted it. These were not obscure corner cases. They were the theory eating itself at its own center. The current anomalies in cosmology have the same character. The early galaxy problem is not an edge case of lambda CDM. Predicting the mass function of galaxies as a function of redshift is one of the things the standard model is most specifically designed to do. The Hubble tension is not an edge case. The Hubble constant is the single most important parameter in modern cosmology, the one that sets the age and size of the universe and connects every distance measurement to a physical scale. If lambda CDM cannot predict both measurements simultaneously, it has failed in its most fundamental quantitative prediction. This historical comparison does not prove that the current anomalies require a revolution of the same magnitude as special relativity or quantum mechanics. Anomalies can be resolved within existing frameworks, as many have been throughout the history of science. But the specific characteristics of the current anomalies, their persistence across independent measurement methods, their growth rather than shrinkage with more precise measurement, their appearance precisely in the most well-constrained predictions of the standard model, place them in the category of anomalies that historically have required framework change rather than parameter adjustment. The relationship between general relativity and quantum mechanics remains the deepest unresolved tension in fundamental physics. Both theories are extraordinarily successful in their domains. General relativity describes gravity, the large-scale structure of space-time, the behavior of black holes, and the expansion of the universe. Quantum mechanics, in its developed form as quantum field theory, describes the other three fundamental forces, the particle physics of matter, and the behavior of atoms, molecules, and the materials built from them. The two theories have each been tested to better than 1 part in a trillion in their respective domains, and they are mathematically incompatible. The incompatibility appears when both theories are needed simultaneously, which happens in the extreme conditions present at the very beginning of the universe and at the centers of black holes. In these contexts, the density of matter and the curvature of space-time are both so extreme that quantum effects cannot be ignored in the gravitational field, and gravitational effects cannot be ignored in the quantum field. Neither theory alone can handle the situation, and no complete theory has been found that handles both simultaneously. String theory is the most developed attempt to unify the two. It proposes that the fundamental objects of physics are not point particles, but tiny one-dimensional strings, whose different modes of vibration correspond to different particles. The mathematics of string theory automatically includes a particle with the right properties to be the graviton, the quantum of the gravitational field, and it is consistent with quantum mechanics by construction. This makes it a candidate theory of quantum gravity. The challenges string theory faces are formidable. It requires extra dimensions, at least 6 beyond the 3 we observe. It predicts a vast landscape of possible universes corresponding to different configurations of those dimensions. It has not produced a unique, verified prediction of any experimentally testable quantity. Physicists have been working on it for 4 decades, and the connection to observable physics remains indirect. Loop quantum gravity is an alternative approach to quantizing gravity that does not require extra dimensions and does not attempt to unify all forces. It quantizes space-time itself, treating the geometry of space as built from discrete quantum chunks at the Planck scale, approximately 1.6 times 10 to the power of negative 35 meters, the smallest meaningful length in a quantum gravitational theory. The Planck scale is so far below anything accessible to current experiments that direct detection of quantum gravity effects is not feasible with any currently imaginable technology. But the structure of spacetime at the Planck scale could leave indirect signatures in the early universe observations Webb and future telescopes are making. Causal dynamical triangulations, another approach to quantum gravity, simulates the emergence of spacetime from quantum building blocks by summing over all possible causal histories of a discretized spacetime. These simulations have shown that a 4-dimensional universe with a positive cosmological constant emerges from the quantum dynamics when the discretization is done correctly. A promising result that suggests the framework may be capturing something real about the emergence of the large-scale universe from quantum principles. What all of these quantum gravity approaches share is a commitment to the idea that spacetime is not fundamental, but emergent. This is the same conclusion that the ADS-CFT correspondence implies. The consistency between these different approaches in pointing toward emergent spacetime is itself a kind of theoretical convergence. The approaches differ in their mathematical structures and their specific predictions, but they agree in their broad conclusion. The spacetime in which cosmology operates is not the bedrock of reality, but a description of reality at scales where the underlying quantum structure has already averaged out. If spacetime is emergent, the question of what it emerges from is central to any complete theory. ADS-CFT suggests it emerges from quantum entanglement in a boundary theory. Loop quantum gravity suggests it emerges from quantum spin networks. Causal dynamical triangulations suggest it emerges from summing over causal histories. These are different answers to the same question, and testing between them requires either experiments at the Planck scale or identifying indirect signatures in cosmological observations. The cosmic microwave background is one place where Planck scale physics might leave an imprint. The quantum fluctuations that seeded the CMB temperature variations were generated during inflation, when the universe was expanding exponentially and quantum fluctuations were stretched to cosmological scales. If the underlying quantum structure of spacetime affected those fluctuations in a way that departed from the standard inflationary prediction, the pattern of CMB temperature variations could carry a signature. Some specific models of loop quantum cosmology predict small modifications to the primordial power spectrum at the largest observable scales, modifications that are potentially measurable with the precision available from Planck and future CMB experiments. These searches for quantum gravity signatures in the CMB are at the frontier of what is technically feasible. The predicted effects are small compared to the dominant inflationary signal, and detecting them requires both high-precision measurements and a detailed understanding of the inflationary mechanism, which itself is uncertain. But the possibility that the origin of cosmic structure is connected to the quantum structure of spacetime is scientifically compelling and technically accessible in a way that direct Planck-scale experiments are not. The Euclid satellite, launched in July of 2023 by the European Space Agency, represents a major step forward in the ability to map the large-scale structure of the universe and probe the nature of dark energy and dark matter simultaneously. Euclid is conducting a wide-field imaging survey of roughly 15,000 square degrees of sky, approximately 1/3 of the total sky, in optical and near-infrared wavelengths. Over its 6-year nominal mission, it will observe approximately 2 billion galaxies at cosmological distances. The survey is designed with 2 primary science goals. The first is weak gravitational lensing, the slight distortion of galaxy shapes caused by the gravitational effect of large-scale structure along the line of sight. By measuring the pattern of these shape distortions across billions of galaxies, Euclid can map the distribution of matter, both visible and dark, across cosmic history. The second is galaxy clustering, measuring the 3-dimensional distribution of galaxies to detect the baryon acoustic oscillation scale at multiple redshifts. Together, these 2 probes constrain the growth of structure and the expansion history independently, providing 2 orthogonal measurements of dark energy and dark matter properties. Euclid's dark energy constraints will be significantly tighter than those from any previous survey, and when combined with DESI data, Planck CMB data, and James Webb observations, will either confirm the DESI dark energy evolution signal or constrain it more tightly. If the DESI signal is real, Euclid data should see a consistent deviation from a cosmological constant. If it is not real, Euclid data should be consistent with a constant dark energy. This cross-check between independent surveys with independent systematic effects is exactly the kind of test that distinguishes real physics from measurement artifacts. The Rubin Observatory, named after Vera Rubin, whose pioneering observations of galaxy rotation curves provided early evidence for dark matter, is under construction in Chile and is expected to begin science operations in the mid-2020s. Its 10-year legacy survey of space and time will image the entire southern sky every few nights in 6 optical filters, producing a dataset of unprecedented breadth and depth. The sheer volume of data will enable statistical analyses that are not feasible with smaller surveys, and the repeated imaging over 10 years will allow the detection of transient phenomena, including supernovae at high redshift. The Rubin Observatory's supernova survey will eventually provide a sample of Type 1 A supernovae at high redshift far larger than any previous survey, enabling the most precise measurement yet of the expansion history at intermediate redshifts. This will directly test the dark energy evolution hypothesis and constrain the Hubble tension from the distance ladder side with greater statistical power than currently available. The Square Kilometre Array, a radio telescope being constructed in South Africa and Australia with distributed antenna stations across both countries, will survey hydrogen gas across a significant fraction of cosmic history, using the 21-centimeter hyperfine transition of neutral hydrogen. Hydrogen is the most abundant element in the universe, and its 21-centimeter radio emission is a direct tracer of the distribution of gas in and between galaxies. By mapping hydrogen at multiple redshifts, the SKA will probe the large-scale structure of the universe at epochs ranging from after reionization to the present, providing independent constraints on dark energy and dark matter that are entirely free of the optical systematic effects that affect galaxy surveys. More importantly, for understanding the early universe, the SKA will attempt to detect hydrogen emission from the cosmic dark ages, the period between the CMB epoch and the formation of the first stars, when the universe was filled with neutral hydrogen that had not yet been ionized by stellar radiation. This era is inaccessible to optical telescopes, but in principle observable in the 21-centimeter signal. Detecting the dark ages hydrogen signal would provide direct information about the initial conditions of structure formation and test whether the Standard Model's predictions for the earliest phase of structure growth are correct. James Webb's own extended mission, which current fuel estimates suggest could continue well past the initial 10-year design lifetime, will contribute to all of these programs. The telescope's infrared sensitivity makes it uniquely capable of spectroscopic confirmation of high redshift galaxy candidates found by wide-field surveys. Where DESI, Euclid, and Rubin find galaxies at high redshift, Webb can follow up with spectroscopy to confirm their distances, measure their chemical abundances, and characterize their stellar populations. This combination of wide-field survey and targeted follow-up is more powerful than either approach alone. The emerging picture of what the next decade of cosmological observation will tell us is one of increasing precision in the specific areas where the current anomalies sit. The Hubble tension will be tested from multiple angles by DESI, Euclid, Rubin, and continued Cepheid calibration from Webb. The early galaxy mass problem will be tested by deeper Webb surveys and by the detection, or non-detection, of even more extreme early galaxies as the observational reach extends to higher redshifts. The dark energy evolution signal from DESI will be confirmed or refuted by Euclid. The large-scale structure violations will be tested by the SKA's hydrogen survey and by the largest optical galaxy surveys. What this precision program will not do, in itself, is tell us what the new physics is. Data constrains theories. It does not produce them. The theoretical work of constructing frameworks that can accommodate all the anomalies simultaneously, while preserving all the successes of the standard model, is being done in parallel with the observational work, and the two are in dialogue. Observations rule out theories, theories predict what observations to look for, new observations rule out more theories, and so on. This iterative process is how physics advances. The timescale for a new standard model of cosmology is impossible to predict. The transition from the Newtonian framework to special and general relativity took roughly 20 years from the Michelson-Morley result to Einstein's 1915 field equations. The transition from classical physics to quantum mechanics took roughly 30 years from Planck's quantum hypothesis to the development of quantum field theory. These transitions were not slow because the physicists involved were not working urgently. They were slow because the conceptual revolution required could not be forced by effort alone. The new framework had to be invented, and invention does not run on a schedule. What can be said is that the observational situation is richer and more constraining now than at any previous point in the history of cosmology. The anomalies are not vague or marginal. They are specific, measured quantities with stated uncertainties, confirmed by independent methods, and growing more statistically significant with time. The theoretical space for accommodating them within the standard model is shrinking. The theoretical work toward new frameworks is active and productive, even if no complete successor has emerged. The combination of these factors makes the current moment one of genuine scientific transition. The period between when the old is known to be insufficient and when the new has arrived. That period is scientifically uncomfortable and scientifically productive in equal measure. The uncertainty is real. So is the progress. Every observation that sharpens an anomaly is a measurement of where the new physics must operate. Every theoretical model that fails to close all the tensions simultaneously narrows the space of what can work. The universe is not hiding its secrets. It is revealing them at the pace that precision observation allows. The telescope is still looking. The data is still coming in. And the answer, when it comes, will need to explain everything that James Webb has found.